Alright, hello everyone, welcome. This is Projects in Docker by Avionics. My name is Ahmed and this is an introduction to the class. Okay, welcome to DevOps. DevOps is short for Developers Plus Operators. This means that deployments are no longer restricted to operators and sysadmins. Code is no more written by developers only. Both teams work together in collaboration to build software in the fastest and most efficient way. Those days, software needs to be built, tested, and deployed in consecutive short iterations to guarantee that it is always up to date with the ever-changing market requirements. Several tools were built in the last few years to address this trend, like for example continuous delivery or deployment. A well-known tool for this is Jenkins. Configuration management, we use tools like Ansible, Puppet, and Chef. Version control by Git, GitHub, and Bitbucket. Instant provisioning by Vagrant, and containerization by Docker. So in this particular class, we are interested in containerization. But what is containerization if you haven't heard this term before? Virtual machines solved many problems and saved a lot of costs, but that was in the past. Today, software needs are increasing. Environments are no longer testing production only. You have staging, you have user acceptance, you have several environments needed by software teams to undergo different tests and scenarios. So you will need a way to minimize costs as much as possible and also to make deployments as fast as possible. So instead of running multiple virtual machines on the same host, consuming a lot of resources, we can run several applications on the same virtual machine. Each will be behaving exactly as if it was having its own operating system, memory, CPU, storage, and other resources. With containerization, you can have 7 web servers, for example, 5 application servers, and 3 database servers, all sharing the resources of one virtual machine or physical server according to how you installed your containerization platform. And when it comes to containerization, the most well-known tool in this field is Docker. Docker is one of the most mature containerization tools today. It is used to run on Linux, but now Microsoft enabled containers in its newest editions, which is Windows 10 and Windows Server 2016. This makes Docker multi-platform. Docker recently introduced Docker Swarm, which allows you to divide your application to small atomic components, each running on one or more containers. This is commonly referred to as microservices architecture. The Swarm engine will orchestrate load balancing, revive crashed containers, and coordinate with other Docker hosts. Docker comes in 2 flavors, the Enterprise Edition, or EE, and the Community Edition. The Enterprise Edition is a paid product, you will pay for support, but the Community Edition is free, so you can always test all the features of Docker, including Docker Swarm, free of charge. So what are we going to cover in this course? In this class, we are going to build a blog web application using the MEAN stack, which stands for MongoDB, Express.js, Node.js, and AngularJS. We will start by creating a simple Docker container model on one host. Then we will move on to creating a Docker Swarm to achieve high availability. Later on, we will make use of Docker Swarm to join multiple Docker hosts to a cluster. And finally, we will have a bonus section about using Ansible to automate Swarm creation. So, what do I expect from you as a student? I expect you to have some Linux background because all the labs and the examples that are going to be run in this class are going to be based on Ubuntu Linux. I also expect some familiarity with Docker. If you haven't used Docker before, that's okay. Section 1 will provide you with a brief introduction about Docker, but the more familiar you are with Docker, the easier you're going to follow in the examples. I also expect some knowledge about virtualization. If you have used VirtualBox or VMware before, that's perfectly fine. As for the bonus section, I expect some background about configuration management tools, not necessarily Ansible. Now I hope you are going to enjoy this course as much as I enjoy teaching it, and see you in section 1. Hello everyone, I would like to welcome you to the first section of our course, Projects in Docker by Avionics. My name is Ahmed and this is section 1. And in this section we are going to take a brief introduction to Docker as a software, what it is, what it can do, how you can use it. We are going to get introduced to the basic commands and tools that we are going to use throughout the projects that we are going to build throughout this class. Okay, so let's first have a quick overview over infrastructure evolution. Long ago, you had to buy a separate hardware machine for every application in your environment. For example, if you are to build an application that is going to be hosted on the web, you'll have to have a web server, an application server, and a database server. all of those were hosted on physical hardware machines. That was a big waste of resources, as you always had to buy servers with high computation power, usually more than what the hosted applications might need. Later on, virtual machines were introduced. Only one powerful server can be used to host the application stack on virtual machines. This approach also had its drawbacks. There had to be a complete OS on each virtual machine. This OS had to consume resources that could be availed for the application instead. Additionally, it required backup, patching, and monitoring, let alone licensing. Portability was another drawback. Moving virtual machines among different hypervisors or migrating them to cloud platforms was not an easy task. For those reasons, the concept of containers was brought to attention. A container is like a virtual machine. However, it does not need a complete operating system of its own. Multiple containers can share a single OS. This frees up lots of resources that can be used by the application. Containers are very fast to boot, very easy to move from one platform to another, like from your laptop to the cloud, to a virtual machine, or even to a bare metal machine. The technology itself is not a new one. It's been used long ago in Unix in the form of BSD jails, Solaris zones, and other forms of container virtualization. However, at that time, it was used only by major corporations like Google. Docker made Linux containers available to everyone. Docker made the technology easy and reachable for everyone, not just big corporations. Docker containers were mainly Linux-based, but recently Microsoft managed to bring containers to Windows Server 2016 and Windows 10. So, what is Docker exactly? Docker is an application used to create and manage containers. Docker can be thought of as the hypervisor responsible for managing and orchestrating the virtual machines, which are called containers. There are two main versions of Docker. The open source one, which is part of the Moby project on GitHub, and the commercial one, developed and maintained by Docker Incorporated. Most of Docker code is written in the Go language, a relatively new systems programming language invented by Google. So, that was a brief introduction to Docker as a whole, what it is, how it is different than virtual machines, and how it can be useful in deploying applications. In the coming lecture, we are going to start installing Docker on our operating systems, on different operating systems. We are going to start with Windows, then we are going to move on to Mac OS and Linux. So, until next lecture, take care. Right, so in this lesson, we are going to start installing Docker on our Windows machine. And because Docker is a relatively new adoption to Microsoft products, it has been recently added to Microsoft Windows as a component or as an installable program. Docker does not work except on Windows version 10 Pro, Enterprise, or Education, 16.07 update, build 14393 or later. You will need to enable the hardware virtualization on your CPU, and this can be enabled in the BIOS settings. This is a hardware setting that needs to be enabled. And you will also need to have at least 8 GB of memory in order to be able to run Docker containers. And last, Hyper-V component must be enabled in Windows 10, but don't worry if you do not know how to enable this, Docker will attempt to enable it during installation. So let's get started with downloading the installer package. So I'm gonna open Microsoft Edge here, and I'm going just to type download Docker for Windows. Okay, and go to the link on Docker domain and click on install Docker for Windows. We have the stable channel and the Edge channel. The stable channel I personally recommend it. It always contains code that has been tested thoroughly and is ready for production. The Edge channel contains experimental features that are not guaranteed to work in each and every scenario. So I'm gonna get Docker for Windows, the stable edition. Okay, I'm gonna start to download it. Okay, the file has been downloaded. Let's open it and press yes. And while the installer is installing Docker,
Community Edition on our Windows machine, let's have a quick discussion of the different versions of Docker that are available. We currently have two editions, or two main editions. The first one is the Community Edition, and that is the one that is available by default for Windows and Mac OS machines. This is the free version. You don't have to pay anything to use this version, but it is, as the name suggests, a Community Edition. This means that the support, okay, let's close the logout. The support that is offered by this edition is the community one. You don't have an official support from Docker. The other edition, which is the Enterprise Edition, it's only offered for Linux as of the time of this recording. And this version includes official support from Docker Incorporated. Okay, so now Docker has been installed for Windows, as you can see from this icon. And if you go here at the tray, okay, you're gonna see that Docker is starting. If you go here at the tray, you're gonna see that we have the Docker icon here. And okay, Hyper-V and containers features are not enabled. We have mentioned this in the prerequisites. I will ask Docker to enable them automatically for me and restart. These are components that must be enabled on Windows 10 in order for Docker to be able to function correctly. And actually, Hyper-V and the containers features on Windows 10 are what enables you to have a Linux kernel under Windows. Okay, and here we are inside after the restart. And as you can see here in this icon, Docker is starting. It's gonna take a few seconds to start. And once it is started, you can just open the PowerShell and run Docker version. And if you have this output, then Docker is successfully installed on your Windows machine. That brings us to the end of this lecture. In the coming lecture, we are going to start installing Docker on a Mac machine. So until then, take care. Okay, installing Docker for Mac is very easy. Actually, it is the easiest one. You can just go to store.docker.com/editions/community/docker-ce-desktop-mac and click on Get Docker. Gonna press OK to download. Once downloaded, just double click on it like this. And as with any application installation on the Mac, you just drag and drop the application in the applications folder like this. And then you can start it by just double clicking on the icon. Next, it's gonna need privileged access. So you're gonna press OK, give it the password. It's gonna take a few moments to start. Just the same thing as we did with Windows. Okay, it's up and running. Let's open a terminal window. And if we run Docker version, you're gonna see that we have client version 17.12 and the engine version 17.12. And they are running on the OS architecture Linux AMD 64. This means that you can run containers that are based on the Linux kernel. You cannot run containers based on Windows, for example, because this is not supported on a Mac machine. As a matter of fact, you can currently run only Docker containers that are based on Windows kernels on Windows machines. Windows Server 2016 or Windows 10 Pro with the minimum versions we mentioned at the previous lecture. Now that we have installed Docker on Windows and on the Mac, let's see how we can install it on a Linux machine. We're gonna start by Ubuntu and then move on to CentOS. So let's open a terminal window. Okay. And first thing we need to do is to enable the apt package manager to download packages over the HTTPS. So I'm gonna type sudo apt-get install apt-transport-https ca-certificates and curl, which is also needed, and software-properties-common. Next command, let's clear the screen. is the command that we are going to use to add the GPG key for authenticating the Docker installation package. So it's going to be done like this: https download.docker.com/linux/ubuntu/gpg pipe2 sudo app key add dash. Okay. Then finally we are going to add the repository itself. Sorry, I forgot a dash here. Okay. Now we're ready to install the application, the package. So let's run sudo apt-get update to update the repositories that we have now. And let's run sudo apt-get install docker-ce, which is the community edition, the one that we are going to deal with throughout this class. Okay, now Docker has been installed successfully. Let's clear the screen, and if you try to run Docker version with your user, you're gonna see that you have only half of the expected output, just the client. You don't have the server output. That is because you are using the local user account or the non-privileged account. You will have to use sudo docker version in order to get the full picture, in order to get the client and the server. And Docker can be actually, and it is recommended to be run by a non-root user. But in order to do this, you will have to add this user to the Docker group. So I'm gonna use sudo usermod-a gcapital docker and the username that I want to add, which is Ahmad, the current user. And in order for this to take effect, I must log out and then log back in by going to this and clicking logout. Then click on my name and log in back again. Now let's open the terminal again. And now if I type docker version without using the sudo command, I am getting the expected output, the client and the server. Let's do the same thing on our CentOS machine. Okay, let's open the terminal. And the first thing we might need to do is to install the prerequisite packages that are required to install Docker. So sudo yum-y install yum-utils device mapper persistent data and lvm2. Okay, and it seems that the CentOS is still fetching automatic updates. Let's kill this process. Okay. Okay, now the prerequisites have been installed. Next, let's add the Docker repository. So sudo yum-config-manager -add-repo, then the URL of the Docker repository, download.docker.com/linux/CentOS/docker-ce.repo. This is the repository that is going to be used for installing Docker. Now once done, you are all set to install Docker by using yum-y install docker-ce. And again, the version that we are going to use throughout this class is the community edition, so it's docker-ce. Okay, now Docker has been installed successfully. Start the service by running sudo service docker start, then sudo docker version. Okay, now we have the client and the server versions, the same thing we did with the Ubuntu. And again, if you want to run Docker with the non-privileged account, and it is recommended to do so, you have to add this user account to the Docker group, and you will need to log out and log in back again. So I'm gonna do just that. Okay, now let's go back to our terminal, and running Docker version without the root privileges is going to give me the expected output. This means that I can successfully run Docker as a non-privileged user. That brings us to the end of this lecture. In the coming lecture, we are going to start actually working with Docker we are going to give it a test drive to see what exactly it can do for us. So until then, take care. Alright, now that we have Docker installed, we are going to use Linux, as mentioned, as our operating system of choice in this class. We are going to do all our labs and all our commands are going to run on Linux. Whether it was CentOS or Ubuntu, both systems are going to accept the same commands. So let's start by defining an image. Docker works by pulling images from some registry or some location. By default, it's located in the Docker repository. And an image can be thought of as a template containing an operating system file system and an application of some type. You can think of it like a virtual machine template or like a class if you are coming from a programming background or if you have worked with object-oriented programming before. An image in Docker is like a class. You create a class and then you instantiate objects out of that class. The same thing holds for Docker images. You pull an image or you create one and then you pull out or you create containers out of this image. So in order to pull an image, the simplest way of doing that is to use the docker pull command. So docker pull, this is the command, and then you give it the identification necessary for pulling the image. The shortest form of a docker pull command will be like this: docker pull Ubuntu. Here I'm using docker as my command and pull as my subcommand, and then I'm giving it just the name of the image. So you might be asking, where would Docker find this Ubuntu image to pull it from? It is not stored locally, obviously. We are working on a CentOS machine, so there is no room for any Ubuntu operating system there. So where does Docker pull the Ubuntu image from? Let's first press enter and see what happens. And notice what happens. It's telling me that it is using the default tag, latest. That is the first thing that was created for us, or that was added for us by Docker. The tag. By default, Docker will pull the image with the tag latest. A tag is nothing but a way to differentiate an image from another, just to mark an image as of some type, some version, or of some flavor. So in our case, we are pulling Ubuntu latest. This command is the same as if I did it like that. Docker pull Ubuntu column latest. If I add a column, I am instructing Docker to pull an image of a specific tag. So let's say, for example, that I have an Ubuntu machine with a tag that is like 17.10, for example, and obviously this might be the version of Ubuntu, or I can have a tag that reads Nginx, for example, or latest-1, whatever tag. You can add whatever tags you need if you are creating an image. We're gonna see how to create images later in this class. However, just understand for now that a tag is just a way to mark an image that it is of some kind. And Docker by default chooses the latest tag for you if you did not supply it already. So if I added latest like this, it's the same as if I omitted it. Docker will always download the image with the tag latest. Okay, so what about the rest of the command? I can easily add here the registry from which I want to pull this image from. So by default, Docker pulls its images from the Docker Hub. Let's have a look at Docker Hub first to see what it is like. So I'm gonna open Firefox browser. Okay, and just gonna head to Docker Hub, just like this. It's hub.docker.com. When I'm inside, can of course create a Docker account for yourself. It's free. However, you can always check for the available Docker images without having to have an account. So here we have the Docker Hub, which is the official repository for the images maintained by Docker. Actually, anyone can have a repository for Docker containers. Actually, there are more than one. The most famous of which, of course, is the one maintained by Docker, and it contains a lot of images. As you can see, there are a lot of images that are available on the Docker Hub. Some of them are official and some of them are non-official, and the difference is that the official images are maintained officially by Docker, while the non-official packages are not maintained by Docker, which means that they are not guaranteed to work in all circumstances or in all scenarios. This is just more of a confirmed image that Docker itself is aware of this image and it is actively working in it. So if I chose, for example, Ubuntu, let's search for Ubuntu, which is the one that we have just downloaded or pulled. As you can see, Ubuntu, and this is the official. Let's click on that. This means that this is an official repository. And as you can see, the docker pull command is docker pull Ubuntu, the same command that we used just a few moments ago. As you can see here, we have a number of tags that differentiate different versions of Ubuntu or different versions of that image. So you have the 1710, you have the 1804, 1404, 1604, and so on. So you can choose whatever tag of those to specifically download or pull the image that you want. Okay, so what if you want to download an image and that image is in a non-official repository? As just mentioned, by default, Docker is going to pull the latest, the image with the tag latest, from the Docker Hub registry and from the official repositories in that registry. So what if you want to download something that is not official? So let's say, for example, that I am searching for MySQL. It's MySQL, like this. I'm gonna see that I have the MySQL, which is the official, and I also have other images that are maintained by somebody else, not Docker. So like this one, MySQL-MySQL-server. This is maintained by a registry that is called MySQL. The owner of this repository is MySQL. Okay, so if you want to pull this repository, notice here the command is a little different. Docker pull, and then instead of just specifying the image name, you prepend it with the owner name. So it's docker pull MySQL/MySQL-server. So that is if you want to download images or to pull images from the Docker Hub. What if you want to pull an image from something else? Maybe you have a website or an FTP site that maintains containers and you want to use it to download a specific image. Or you may have subscribed to a third-party container repository like the one maintained by Google, for example, or any other entity, and you want to use that for your download. In that case, you are going to prepend the image with the URL of the repository. So for example, if you are using quay.io to download or to pull an image that is called Ubuntu, you're gonna do it like this: docker pull quay.io / the repository name. Let's say, for example, it was Ubuntu repo, for example, /Ubuntu. So this is effectively giving the full path for the image, starting with the registry name, then the repository name, then the image itself, and of course, optionally, you can add whatever tag you want to specifically target this image. So now that we have successfully pulled a Ubuntu image and we had an idea about how images are stored and how you can pull different sorts of images, let's see how we can create a container out of that image. In order to create a container, you will need to run docker, but this time I'm going to give it a different command. Let's just clear the screen to give you a better view. Docker run. Docker run is used to create containers out of images. So docker run, and I'm going to give it two flags, -i and -t, and both of them can be combined together as with any Linux command. So it's -it together, and then you're going to give it the name of the image that you have just pulled, optionally followed by the tag of that image, because you can download several versions of the same image, provided that you specify different tags for each one. So I can have Ubuntu latest, and I can have side by side Ubuntu 17.10, Ubuntu 16.04, and others, all on the same machine. So docker run -it Ubuntu latest, and then I can specify a command that is going to be run on that image, or technically speaking, on that container. If I press enter, a few seconds, and I'm inside a shell prompt that is different than the shell prompt that I was in. As you can see, it's giving me root @ and then a combination of characters and numbers. This is the container. We have successfully created one, and we are actively inside it. We are literally inside a shell that is running or that is hosted on that container. If you want to prove, let's run any command, like for example cat /etc/os-release. You can see that it's giving me the name is Ubuntu, the version is 16.04.3, which is the version of Ubuntu that is running on that container. And the rest of those data are just related to that specific OS version. Okay, so let's run ps-ef. You can see that I have only 2 processes running, and technically speaking, I should be only having 1 process running, which is /bin/bash, because this is the process that we have instructed the container to run. ps-ef is just the process that we have created for a fraction of a second, just to give us an overview of the processes that are running on the system. So this process has already gone by now, and the only process that is running continuously in the background is /bin/bash. And that deserves a little explanation. A container will continue to run as long as a command is running, like this, bin bash. If this command ends, the container will terminate. Let's see that in action. I'm gonna press Ctrl plus P and Q in order to exit from the container without killing /bin/bash. Again, it's Ctrl plus P plus Q plus letter P and letter Q. That will let you exit out of the container shell and still run the container in the background. So how could you know whether the container is still running or it is terminated? Let's clear the screen. Easy enough, you can run docker container ls. This is gonna give you an overview of all the containers that are running on your system. So here I have a container ID. That is important. You will need to take a look at that ID because this is the one that we saw when we were logged in the shell, in the container shell. This was the ID that was typed in the prompt. Then I have the image name on which this container is based and the command that is used to keep this container open, created 2 minutes ago. Status, it's up 2 minutes ago. It has no ports, and this is a friendly name that Docker gives to any container for which you do not specify a name. We're going to see how to specify a name for the container later on in this section. But now the only thing that I need you to understand is that a container will only run if and only if there is a command that keeps it running in the background. So now that we have exited out of that container, let's say that we want to connect back or to attach back to that container. In order to do that, we can run docker container. This time we're not gonna type run because run is gonna initiate or launch another container. I'm going to use the exec command. The exec command is going to execute commands against that container, and I'm gonna pass it again. Then I'm gonna give it the container name or the ID. Since I did not supply a name for that container, I'm gonna use the ID. So I'm gonna copy the ID and paste it here. Then again, I'll have to type or specify the command that I need to run in that container. So it's bin bash. Again, I'm inside that container. Now, if you're wondering what those I and T represent, -I is for interactive and -T is for terminal. I am instructing the container to run in the interactive mode, because by default, the container, as we are going to see later in this section, a container often runs in the background because a container supplies a service, like for example, a database or an application or a web server. So it often runs in the background. Here, I wanted to run in the foreground in an interactive mode so that I can interact with it. I can run commands directly into it. And the T is obligatory here because I will need to attach my terminal to the containers, so I'll have to use both of them together, -I for interactive and -T for terminal, to be able to attach my terminal to the container's terminal and target a command like this, /bin/bash, which is the bash shell. Okay, so now let's exit, and let's again run docker container ls. Okay, in order to stop this container, you will need to run docker stop, then give it the container name or ID. So I can get the ID again, copy and paste. This is going to stop the container. If I now run container ls, I'm going to see that I have no containers running. The output is empty. If I want to have a look at all the containers that are on my system, including the ones that I have stopped, I need to add a -A to the command. Now I have the container that I used to run. It was created 9 minutes ago and it exited 13 seconds ago, just when I used container stop and I gave it the ID of the container. Now, if I want to start it back, I can easily use docker start, then give it the ID of the container, just like this. Now the container is back. Let's remove the A to ensure that it is running. Yes, it is running, and I can easily connect to it again using the same command that I did before, and I am inside. Okay. If I want to completely remove that container from my machine, let's clear the screen. I will have to first stop it. So I'm gonna use docker stop followed by the ID of the container, then docker container rm, and then give it the ID of the container, and then it is gone. Now if I typed docker ls, it's gonna give me nothing. Even docker ls-a, it's gonna also give me nothing. The container was completely removed from my machine, but the image is still there. If I want to remove the image as well, I will have to use docker image rm, then the name or the ID of the image. And if you want to get it, you can either use the name of the image, which is Ubuntu, or you can just use docker image ls like this. It's going to give you the images that are currently installed on your system. Here is Ubuntu from the repository Ubuntu. The tag is latest. This is the image ID, and this is the size and the creation date. And that creation date is not the creation date on your machine. This is the creation date on the repository from which you downloaded or pulled that image. This image has been created 10 days ago. Now if I want to remove that, I can just use docker image and rm, and I can either give it the name or the ID of the image like this. Now it has removed the image with all the layers that this image contains. We're going to talk about layers later in this class. But now if I type docker image ls, I will have nothing. Okay. That brings us to the end of this lecture. In the coming lecture, we are going to see the more advanced part of Docker, which is how to create an image yourself. So until then, take care. Alright, so far we have seen how we can download or pull an image and create a container out of that image. And that container will act just like a virtual machine on our system. We can access it, we can connect to it, we can run commands against it, and so on. But that is not why Docker was created, and that's not how Docker works in real production environments. You usually download an image that provides some sort of functionality, like for example a running application, a running web server, a running database server, and so on. Then you run a container or more out of this image and use those containers to build an application stack. In the previous lecture, we saw how we downloaded the Ubuntu image from the official Docker Hub repository, and we used it to create just a bash shell on our system. Let's do something that is more exciting. We are going to create a web server using the Light HTTPD server, or Lightly as it is called. It is a lightweight web server. We will create an image that will provide this web server, and we are going to also create a simple index.html file that is going to serve by the container based on that image. In order to create this image, we will need a base image on which we are going to place our Light HTTPD server. We are going to use the Alpine image. Let's have a look at this Alpine image first. I'm gonna use docker pull Alpine. Alpine is a version of Linux, a very minimal version of Linux. It is just 4 megabytes in size, as you're gonna see here. The FS layer is just 2 megabytes in size. When it is uncompressed, it is less than 4 megabytes in size, and it provides the bare minimum functionality that a Linux machine may have. So let's first create a container out of this. So I'm gonna use docker run-it. Can optionally specify a name here. I can say the name here is minimal, and the image on which this container is gonna be based is the Alpine that we have just downloaded, and I will need to run /bin/sh. And notice here that I am using the /bin/sh rather than bash. That is because, as I have just mentioned, the Alpine image is a stripped down version of Linux. A lot of things have been removed, including the shells that are available, including the bash shell. You are only left with the Bourne shell, which is /bin/sh. When I'm inside, I can type /cat/etc/os-release. As you can see, Alpine Linux ID is Alpine, and that's it. It's a very small image, very lightweight, okay? But it has everything that a typical Linux system requires. Let's exit, clear the screen, and we are going to use this image as a base for our Light HTTPD server image. So in order to do that, let's have a quick discussion about how an image is made up of. An image in Docker is made up of several file system layers stacked over each other. every time you add a functionality or you add a file to your image, a new layer is created and is stacked above the previous ones. Docker is responsible for making you view this stack of layers as if it was just one layer, one file system, and it is serving everything that is underneath it. So, for example, you might have a web server that is having one layer running the Ubuntu, another layer running the Apache web server, and if you have PHP installed, you might have a third layer running PHP and so on. If you have an image that is made up of those three layers, you will view this image as if it was one file system that contains Ubuntu, Apache, and PHP, just as if they are one machine. So in order to create an image with this concept, we will need at the minimum a file that is called Dockerfile. So in order to create an image, let's create a directory. I'm gonna call it LightWeb for the name of the image. Let's get inside it. And as mentioned, you will need to have a file that is called Dockerfile. Notice that it is named exactly this way, Dockerfile with a D capital and Dockerfile without any spaces. Press enter to get inside this file. And inside this file, I'm gonna type the first command from Alpine. From Alpine instructs Docker that it is going to fetch the layer of the Alpine image. So it's gonna use the base of Alpine, and then after it grabs this, it's going to run. So I'm giving it the keyword run apk add, which is the command used by the Alpine Linux flavor to install light httpd. Okay, so here I'm running the command. It's apk and add --update light httpd. This will update the repositories and install a package that is called light httpd. Then I will need to add some configuration to my web server in order to let it run correctly. So for that, I will have to create that configuration locally on my machine and copy it to the image when I'm building it. So I'm going to use the copy command for this. And I can write it in small letters, it won't matter. But just to keep things consistent and to differentiate between commands and arguments, I'm going to use uppercase for commands. I'm going to copy everything from /etc/light httpd. This directory is yet to be created. I'm going to copy everything inside this directory to /etc/light httpd on the image. This is for the configuration. I'm going to also copy the web files from var/www/html. Again, this directory is going to be created later on. I'm going to copy everything under this directory to /var/www/html on the image. Finally, I'm going to expose 80, which is the port that I will need this image to expose when a container is run. And finally, I am going to type in the command that is going to let this container run in the background. So it's light httpd. This is the command itself. Notice here that I'm adding it inside a list with the command and the argument separated by commas and quoted in double quotes. So it's light httpd-d for the daemon mode -f for the configuration file, and then I'm going to point to the configuration file that I've just copied, which is under /etc/light httpd/light-httpd.conf, like this. Okay, and that is your Docker file. Let's save it. And now we need to create the directories that we have referenced inside that Docker file. So we have /etc/light httpd. I'm using mkdir-p in order to create any missing directories in the tree or in the path that I'm going to specify. So I'm going to create the /etc/light httpd. I'm going to also create the var www/html directories. And the reason I'm doing this is just for consistency. I could have placed everything inside the root directory like this, and I could copy it one by one to their respective directories on the destination image. But this makes things consistent. This makes me always know which file belongs to which location. So let's now create the configuration file that is needed to start light httpd. I'm going to call it light httpd.conf. as it is mentioned in the Docker file. Inside it, I'm gonna just write the minimum that is required for this web server to run. So the server.document root, which is the location from which web files are going to be served, is /var/www/html. Server.port is 80. Server.index files, which is the file that will be served when no file is requested in the URL. Instead of displaying the contents of the directory, it's going to display the contents of this file if it exists. Then finally, you can add MIME types.assign, which is the MIME types that this web server is going to serve. And we don't have a lot, just .html. It's going to be served as text-html. That's enough for now. I could have added, of course, other MIME types. The list could go very long, and a configuration file for light HTTPD server can become very long. I'm just giving it the bare minimum to start. Let's save, and now let's add the file that is going to be served by our server. So in var/www/html, I'm going to create a file that is called index.html. Inside it, just add some minimal HTML like this. HTML body h1. Welcome to light HTTP server. That's like that. Let's close the body and close the HTML tags. And now I have everything in place. Now I can build whatever I want inside a Docker image and automatically import that image to the list of images that I have locally on the machine. So in order to do this, I'm going to use Docker build -t for the tag. And here I can name my image whatever I want. So I'm going to call it light web, just like the name of the directory. This is the best practice, just to know which directory serves which images. And I can optionally add a tag, so I can add v1, for example. Then a dot. A dot means that I want to apply this on the current directory, which contains the Docker file. Press enter. And pressing enter is going to execute the instructions found in the Docker file. It's going to download and install light HTTPD package. It is going to copy whatever was inside etc light HTTPD, which is the configuration file that we added. Also, anything under var www.html, which is the index.html file, to the respective directories in the image. Then it is going to instruct the container to run this command whenever it starts. Let's clear the screen, and now if I run docker image ls, I'm gonna see that I have a new image that has been added, which is light web. Here, as you can see, it's here, and its size is only 13 megabytes. That is because it only contains the Alpine package and the light web server. Notice here the difference between a virtual machine and a container. A virtual machine, just to serve light web HTTP server like this one, is going to be multiple times larger than this. It's going to be at least 1 gigabyte in size. Why? Because you will need to install a fully fledged operating system like Ubuntu or CentOS, for example, and you are also going to install this package on top of it. But here I'm having a stripped down version of the operating system. Most of the things that you don't need for this application to run are just not shipped. They are just not there. They have been removed. So you have the bare minimum to start an application, and you are effectively consuming very less resources in terms of storage and also in terms of CPU and memory. Okay, so now let's run a container out of this. So we are going to run docker run -d this time. -d means that I'm going to run it in a detached mode, or in other words, I'm going to run it in the background. I don't want to attach a terminal to this container. And --name, let's give it a name, my light HTTPD. And notice here that this container exposes a port. This means that you will have network access to this container. So I will need to inform my host about this port by adding the -p, and -p here is going to have the source port on the host, which is 8080, and the destination port on the container, which is 80. This means that if I want to access port 80 on the container, I'll have to use port 8080 on my host. And then you give it the name of the image, which was light web, just like that. And notice here that when we forgot to add the tag, it is giving us unable to find image lightweb-latest locally. That is because I will need to add :v1 because this image is having the tag v1. So as a rule of thumb, always remember to add the tag at the end of the image name, just in case, because maybe you want to target a specific tag, and forgetting to add the tag will automatically let Docker pull and initialize the latest tag of the image. So running the command again with the correct tag. Okay, now we have a container. This is the ID of the container. This is the long version of the ID, because if you run docker container ls, you're gonna see that this is a stripped down version of this ID, and you can always use that ID instead. Now I have Lightweb version 1 or v1 running with this command, and if I want to check it, all what I have to do is just go to Firefox and navigate to localhost -8080. Okay, and this error means that we have something wrong with our MIME types. So let's cancel and go back to the terminal. Let's go to ESC and lighthttp.conf. Okay, there's a typo here. It's MIME type, not MIME types. Now we're gonna have to build this image again, but before we do that, we will need to stop the container. So docker container ls. Let's take a copy of the container ID and use docker stop, then the ID of the container. Let's make sure that it is gone. Okay, now I will need to build the image again with the changes that I did to the file. Okay, let's clear screen, and now I will run the container again. Okay, notice here that it is giving me this error that we have a conflict. The container name mylight_httpd is already in use. So in order to create another container with the same name, you will have to remove the container that you have just stopped. So I not only have to stop the container, but also remove it completely from my system in order to be able to run again a container with the same name. Notice the difference. Okay, now it is running. If I type docker container ls, I'm gonna see that it is running again. And let's go to the browser. Let's go to localhost :8080. Okay, now I have welcome to Light HTTP server. We have successfully created a web server using a container. It is using just 13 megabytes of storage. So that was just a quick introduction to Docker, what it is, how it can be used, and the main difference between using Docker and using virtual machines. In the coming sections, we are going to start developing a project in which we are going to see later on more and more features of Docker. We're going to dive deeper into Docker commands, how the images are created, and how the storage is being managed, networking in Docker, security, and other aspects. So until next section, take care. Hello everyone and welcome back. This is a new section in your course, Projects in Docker by Avionics. My name is Ahmed, and in this section, we are going to start deploying our main application using Docker. The application that we are going to deploy is the MEAN stack. MEAN stands for MongoDB, Express.js, Angular.js, and Node.js. The interesting thing about the MEAN stack is that all the components use JavaScript as the coding language. Docker will help us deploy this application using the microservices architecture. In this architecture, the application components are decoupled from each other. So, our application will have a backend database running MongoDB on a container. This will be responsible for saving and retrieving data off the disk. The application server will handle the application logic on another container. It will interchange data with the backend database, and it will provide an HTTP API for the web server to connect to using AJAX requests. Data will flow from and to the application server over HTTP using JSON. The application server will be running Node.js with Express.js to provide the necessary API interface. Finally, the web server will be running on a third container, and it will contain the HTML, images, CSS style sheets, JavaScript, scripts, and any other static files. The application we are going to deploy is a very simple blog. The web server will handle all the static files. We will use Nginx for this, which will act as a web server and a reverse proxy at the same time. A reverse proxy is used to route specific requests to a back-end server. Any requests that require database connection has been grouped into URLs that start with /API. Angular.js will make the necessary AJAX requests. Nginx will automatically route such requests to the back-end application server. Angular.js then will handle the reply and generate the necessary HTML. Now let's have a look at the benefits of this microservices-based architecture. You can easily switch the application server to run any other engine other than Node.js, for example Python, Django, or Flask, PHP, Laravel, Ruby on Rails, or any other service, as long as it will respond to the API requests and provide the output expected by the front-end server. Same thing holds for the web server. You can also switch to any other technology that provides a web server and a reverse proxy. Second, if the application server or the database server is down for some reason, you don't have a complete outage. At least the visitors will see a nice error message that servers are under maintenance instead of cannot connect to server. Front-end developers and back-end developers can work simultaneously without interfering with each other's work. You can easily scale any component by adding more containers and making a cluster without affecting the other components. So as you can see, Docker here and the concept of containers can help us easily and effectively deploy an application using the microservices architecture instead of the monolithic traditional architecture. In the monolithic architecture, you would have only two servers and sometimes only just one server with everything deployed on it, the HTML, the programming language or the application server, and the database. But using a microservices architecture, as you can see, you can deploy each component on its specific container, and as you can see, Docker makes this very easy. So that was an overview of the project that we are going to work with in this section. In the coming lecture, we are going to start the actual work, so until then, take care. Alright, so let's get started. First thing, we are going to create a directory for our application, so let's go to Documents. Going to make a directory, let's call it mean in all caps. Let's get inside. And we are going to create 3 directories for the 3 images that we are going to create using Docker. So let's create a directory that is called db, another directory that will be called app, third directory that will be called web. Of course, needless to say, the first directory will be holding the database image, the second one is going to hold the application image, and the third one is going to hold the web server image. I'm going to start from the down upwards, so I'm going to start with the database. Let's get inside the database. And the database actually is the easiest one. We just have to install the MongoDB. So let's open a Docker file or create a Docker file. And let's start adding the instructions that will install the MongoDB. So the first thing we're going to do is that we are going to specify the image that we are going to base our image on. Remember from the first section we said that the Docker image is nothing but layers of images stacked over each other. So we are going to use the Mongo image, and we can add the tag that specifies the edition of this image, which is 3, Mongo 3. And then we are going to run apt-get update-q for quiet and apt-get dist upgrade-y and apt-get clean, and finally apt-get auto clean. So what does this code does? If you have worked with Ubuntu before, this will update the repositories to the latest, and this will make a distribution upgrade. It will upgrade about Ubuntu, which is the image on which MongoDB is based. And this is just in case if a new dist is available, we are instructing the image to update to the latest Ubuntu distribution when it is being built, just to ensure that we are at the latest possible level. and then apt-get clean and apt-get auto-clean. This will ensure that any obsolete packages are not available on the system. All of this is just to make the image as small as possible, and this is one of the advantages of using Docker, which is that the image does not consume much space as the full operating system. If you have a Ubuntu operating system, it might take 1 or more gigabytes of size. Using a Docker image, we need to make this image as small as possible. So because of that, we are cleaning any obsolete packages or any unused packages using those commands, apt-get clean and apt-get auto-clean. And you might be asking, why did we put the command that way? Why wouldn't we just use something like this? Run apt-get update, and then on another line, run apt-get dist upgrade, and so on. That is because each command of those will add a new layer to the image. The image is based on a layered file system. Each command of those is going to add a new layer, and this will unnecessarily increase the image size. So putting them all in one command will ensure that only one run statement is going to be executed, and this will ensure that our image is kept at the minimum. Okay, so let's save the Docker file. Let's go to our directory and let's run our docker build command. So it's docker build -t for the tag, as we have learned in the first section. Then let's give it a name. So the name, by convention, should be the name of the directory. Then dot to indicate that we are going to build this image based on the Docker file that is in our current directory. Press enter. As you can see, it is grabbing the image from Mongo. It is pulling all the file systems, all the layers of the file system. These are the layers that we have talked about. Every run command, every copy command is going to add a layer to those. And as you can see, each layer can significantly increase the size of the image. So let's give it a few moments to complete. I'm going to speed up the video here. Okay, and now the image has been built successfully. If I run docker image ls, I'm going to have, as you can see, the Mongo, which is the base image on which I built my DB image, and the DB image itself. So what's the difference? Why we have 366 megabytes for the Mongo image, which is the base one, and 377 for the one that we just built? That is because we use the apt-get upgrade and apt-get update to download and install any new packages for the system. So that is the reason for that slight increase in the size. Okay, so now we have this image. We are ready to start creating containers out of that image. And that brings us to the end of this lecture. In the coming lecture, we are going to start building or deploying the second tier of our application, which is the application tier. So until next lecture, take care. Alright, so now that we have our database image built and ready for creating containers, let's start deploying or building our application image. As we have mentioned, the application image is going to be based on Node.js application server. We are going to create an API out of this application server, and it is going to serve the web server using JSON. So let's move one step back and create a directory that is called app. Okay, we have created it already in the previous lecture. That's okay. So now let's create the Docker file. Okay, so in the Docker file, we are going to need more than just building the Node.js app or installing Node.js. We will need to add some application files. We will need to make some modifications. So our Docker file will look something like this. From Node, which again is the image that will be used as a base for this image, or the image that we are building, and the usual run apt-get update -q and apt-get dist upgrade and -y and apt-get clean and apt-get auto-clean. We already explained what this line is for and why we are putting it in one line instead of several lines in the previous lecture. Okay, the next thing we're going to do is that we are going to use the expose keyword in Docker file to instruct the image that is going to be exposing or listening at a port, we are going to choose port 3000 for this application. Node.js can listen on any port that you want. However, you should always pick ports that are more than 1024, because anything that is less than 1024 is going to need root privileges to start listening for connections, and we do not need the image to run as root. We need it to run using the node user, so we need to choose any port that is higher than 1024. So we chose port 3000 for this lab. And then I'm going to add an environment variable indicated by env for environment. Environment variable is just, as the name suggests, a variable that can be used inside the Docker file. So I can define app path. This is the path that our application is going to use. I'm defining it here as a variable so that we can use $app_path in the rest of the file instead of just repeating the path. So our path is going to be /usr/share/app. This is the path where our application will live. If you haven't worked with Node before, it's very easy. It's just one JavaScript file containing some instructions, and Node can run this file as an application server, and it can listen on whatever port you instruct it to. So this is the path where our files are going to reside. And of course, this file must exist first on the image. So I'm going to ensure that it does exist. So I'm going to mkdir-p app path, and going to also ensure that this path is owned by node user and node group. And notice here how I am adding it again on the same line, so that, as we mentioned before, if I typed another one statement here, it will add an unnecessary layer to the image, increasing its size without actually needing it. Okay. Next, I'm going to use another instruction of a Docker file, which is workdir. Workdir is as if you typed cd some path. Okay, if you type cd and you type the path to some file or directory on bash shell, you are going to be standing or working in that directory. So workdir ensures that as if the image, or as if Docker has typed cd and then it typed the path that you are going to instruct it to, which is app path. So my working dir now is /usr/share/app. I'm going to use this instruction user node. So now I did two things. I have changed my working directory to be /usr/share/app, and I'm using user node to run whatever commands I am instructing the image to do. It is going to copy everything in this directory to $app_path. Don't forget the trailing slash. Then it is going to run npm install. npm, if you haven't worked with Node before, is like the package manager for Node. It is used to download and deploy any packages that Node needs to start working correctly. In this particular lab, we are going to use some packages like express.js, and those packages will be placed in a file that is called packages.json, and npm will examine the contents of this file, and it will automatically install any packages inside this file with the specified versions. So that needs to be done on the image while it is built. And we can also use the npm command in order to actually start Node, like this. So let's save the file, and let me explain briefly how Node works. So here we are in our working directory. And for Node to work, the first thing you're gonna need is that you will need to have, as I just mentioned, a file that is called package.json. So package.json will contain JSON formatted data for both the metadata of the application, like the name, the version, how to start it, and so on, and also the dependencies. Actually, we are interested here in the dependencies more than the metadata, but we're gonna write both. So the name of our application, we're going to be projects in Docker, or PID, like this, PID_blog, and version, let that be 1.0, for example. And scripts, we're going to have the start script using node server.js. We're going to create that server.js shortly. Then this is the metadata of the file. Let's move on to the dependencies, which are more important here. Dependencies. we are going to need express.js, which is a package used by JSON to handle several web requests. It is actually very common for those who use Node.js to develop web applications. We're going to need it here to help us create the API that we need. The version of this is going to be 4.15.4. We're also going to need body parser. Don't worry if you don't understand what those packages do, don't worry. We are interested here in how Docker deals with them, not how they work. So these are just packages that are used by Node to create the necessary API that we need. Finally, Mongoose, and Mongoose is the package that is needed by Node.js to be able to connect easily to MongoDB. Okay, and that's it. Okay, now we have a package.json file. Now notice a very important thing here. In the Docker file, we mentioned that we need to run npm install on this, or by default it runs on package.json. But actually npm install takes a considerably long time to download and deploy the necessary packages. And npm will eventually place those inside a directory that will be created here. It's going to be called node_modules. So a trick that I have learned is that we can run npm install. Of course, if you have Node.js installed on your host, you can just run npm install here on this directory before deploying it to the application. After all, the application will use everything that is inside this directory, including package.json. So if I run npm install here, it is going to install everything in the package.json file and place it inside this directory. So apparently we have something wrong here. The version here should be 0.0.1. Let's go back and run npm install now. Okay. Now if we examine the contents of the current directory, you're going to find that we have node modules. The node modules contain everything that is needed by Node to run the application with the code that we are going to supply. Next thing we need to do is create our server.js file. This is the file that will be the bootstrap of the application. You don't have to understand it, just the important parts here is that it's going to use port 3000, as you can see here. So it's going to use either the port provided by an environment variable, or it's going to use 3000. And the other important thing here is the URL by which it is going to connect to MongoDB. MongoDB is running on another container, and notice here that this is the IP of the container. At the end of the section, I'm going to show you why we have chosen that particular IP address and not any other. This is the database that is going to be created automatically for us. So I'm going to call it posts, and this is how Node.js can talk to MongoDB using this form of URL, MongoDB : / and the IP address where MongoDB is installed, which is the IP address of the container that we are going to create out of the MongoDB image, then the database name. This database is going to be created if it does not already exist. Next, we're going to use some files, controllers, and views. This is not, of course, because this is not a Node.js course, so I'm not going to go through the details of this. I'm just going to copy and paste those files into our current directory, and you're going to find all the source code in the resources folder that accompanies this section. So if you have a look here, I have pasted a directory that is called API. It contains controllers, models, and routes. These are what makes Node.js work. We will need to copy this entire directory into the /usr/share. Let's look at the Docker file again. All this is going to be copied inside the application path, which is /usr/share/app. Once these are copied, we can run npm install in order to install anything that might be missing from the package.json or that might have changed. Then we're going to use npm start to start the application out of server.js file, which is actually inside the same directory here. I hope everything is clear, and it's going to get clearer once we start running the containers and launching the application. Okay, so now let's go ahead and build our image. Let's have a look at our contents of the contents of the current directory again. The Docker file, the API containing the application files, node modules that we have opted to install offline before copying them to the image, package.json, and server.json. Now let's run docker build -t. We're gonna call it app. We're going to omit the tag, and it will default to latest. Of course, you can add whatever tags you want.
and then add the dot. Okay, so now the image has been built successfully, and these lines in red here show that the npm install has been run. That is the default output of npm install when there is no description or repository or license fields. Actually, I've managed to make the package, the JSON file, as brief as possible, just as not to distract you. If we clear the screen now and type docker image ls, you're gonna see that we have now Mongo image, the base image, node, the base image, and then the two images that we have built on top of them, the database or DB and app. That brings us to the end of this lecture. In the coming lecture, we are going to build a final image of our stack, which is the web server running Nginx. So until then, take care. Okay, now we are going to build the final image in our stack, which is the web server image. And as we mentioned at the start of this section, we are going to use Nginx for this. So let's go to the web directory and let's start by, as usual, creating the Docker file. Okay. Now here we are. The Docker file of our Nginx is going to contain the following. As usual, we're going to use the image on which we are going to base our image. It's going to be the Nginx. And of course, we're going to run our usual apt get update, apt get dist upgrade -y, apt get clean, apt get auto clean. Okay. But in this particular image, we are going to add another command. We are going to install the OpenSSL package. We are going to need it, as we are going to see later in this project, because we are going to use it to create the password that we are going to use to protect some parts of our web application. So OpenSSL is a needed package in this image, so we're going to use apt-get to install it. It's apt-get install OpenSSL. Okay. Then as usual, we can define an environment variable that is going to define our web path. We're going to call it www_path. It's going to be in /usr/share/www/html. And you can use whatever path you desire, as long as this path exists. And in order to ensure that it does, we will need to create it. So mkdir-p $www_path. And change ownership, Nginx for the user and the group for www_path. And if you are not familiar with shell commands, if you are new to Linux, this and sign means that we are instructing the image to execute this command only if this command is successful. So if for some reason or another the mkdir command did not complete successfully, the directory is not created for any reason, this command is not going to run. It's just a way of combining commands, one way of chaining commands together, but we need to ensure that all of them are completed successfully before going ahead. Now we are going to create the password for the .htpasswd file for our authentication. The htpasswd file is a file that is used by Nginx to protect some parts of the website or the website as a whole. It contains users and passwords encrypted in some form, and it is used for basic authentication. So I could have just created inv password for a password variable, and I could have set it to something like this, pass. However, I need this to be configurable while building the image. I will need to give the user the chance to supply the password while he or she is building the image. So for this, I'm going to use another instruction, which is arg or arg. Arg is going to give you an argument and a default value for this argument, but this can be overridden while building the image. So how can we override this? Simply by adding --build -arg. Let's add this as a comment so that it does not show that red highlight. --build -arg allows us to add command line variables or command line arguments to the build command, like this password equals pass123, for example. So I can write the whole command as follows, like docker build -t, then give it this build argument, then dot, as usual. I'm gonna leave it here
for you just as a reference so that you always know why we used arg instead of the inv. Okay. Next, I'm going to run the following command to actually create the .ht passwd file using a shell command. I'm gonna explain it while I'm running it. Printf, as the name suggests, it's gonna print a line. So it's user, and this is the user. Its name is user. I can add anything like Bob, for example. Okay, and then I'm gonna have to create the password. This can be done by using this notation, $sign followed by a pair of rounded brackets. Then open SSL, the command that we have installed at the top of this file, passwd-1, then the password. So the password is going to be read either from this default value or from this argument if we passed one. If we did not pass anything, if we did not pass build arg to the build command, is going to take the default, which is pass. If we did, it's going to take whatever was supplied in the build command. Okay, then we need to add \n for new line, and we are going to add this to the www_path in a file that is called .ht passwd. Now let's break this line and see what it exactly does. So printf, as we said, is going to print a line. This line is going to be amended by using this double greater than sign. This means amend or append at the end of the file. And this is the file that we are going to create if it does not already exist. If it does exist, it will append to the end of it. It's called .ht passwd file. Okay. And it's going to reside in the www_path, which is the /usr/share/www/html. Okay. So what is going to be added to this file is this line, Bob as a user, followed by the hashed password of Bob. In order to hash the password, we need to run this command, OpenSSL passwd-1, and then the password itself. This is the clear text password. It's going to be read from the command line or from the argument default value, which is pass. Then we need to add a new line. So imagine that this password was just something like this, an encrypted password. It will be added to the end of this file. So why did we add the $sign and double brackets? This is because we need to execute the content that is between those brackets. Instead of just adding it literally, I need to encrypt the password and add it here. So whatever comes inside those brackets is going to be substituted by what this command yields. In other words, the encrypted password. So the ht passwd file is going to contain something like this. I'm going to show it to you when we run the container out of this image. Okay, now we need to start configuring Nginx. We need to create the configuration file needed for running our web server. So the first thing we need to do is remove the default configuration. So we are going to run rm/etc/nginx/conf.d. This is the default place where the configuration file of Nginx exists. So we're going to delete default.conf file located in /etc/nginx/conf.d. And we are going to replace it with our own version. We are going to copy whatever was inside etc nginx/conf.d main.conf. And what I'm doing here is that I'm going to create a file system or a path that is similar to what is exactly on Nginx. As we said, this is just by convention to give you an idea about where the file that you are creating will reside on the image. So I'm going to create after just after I finish the Docker file, I'm going to create etc/nginx/conf.d, and I'm going to place main.conf inside that path, and then instruct Docker to copy that file once I build the image to nginx/etc/nginx/conf.d, just like that. And finally, I need to copy the web files itself. I'm going to have to get them. They will be located in /usr/share/www/html to the corresponding directory on the image /usr/share/www/html. And that's it. That is our Docker file. And again, this is available for you in the resources that accompany this section. Now that we have finished creating our Docker file, let's add our configuration file and get our web files, the HTML files that are going to make up our blog. So let's go to our terminal And while we are inside the web directory, I'm going to create usr share www html. Going to also create etc nginx conf.d, and then I'm going to go to the web directory and just paste the web files. I have already downloaded and modified those files from a repository that I found on GitHub. I made some modifications to the website so that it can work with Node.js. So I have now pasted them. As you can see, we have some Angular views, we have some HTML files, we have some JavaScript files, CSS files. Can have a look at this when you download the resources files that accompany this section. Now let's go to create our configuration file. So let's go to etc conf.d nginx conf.d, and let's create our main.conf file. Okay. The configuration of nginx is very simple. Just create a server object. Inside it, we're gonna listen at port 80. Gonna specify a server name, although this is not that important, but we can just specify any name. Let's say projects in docker.local. It's not gonna be used anyway. And we're gonna specify the root of our files or web files. Gonna be in /usr/share/www/html. Of course, that's gonna be created when our image is built. And the index of this web server is gonna be index.html. Don't forget to add a semicolon at the end of each statement on nginx. Failing to add so is going to give you a very hard to find error. Now we can define our locations. Each location in nginx can be defined using the location keyword. Every path can be defined by the location keyword. So first thing I'm going to do is that I'm going to deny downloading anything that starts with a dot, just to prevent users from downloading the .htpasswd file. This is my first location. My second location is going to be our create.html file. This is the file or the page that is going to be used to create new blog posts. I'm going to instruct nginx that this needs to be protected. So this is the message that is going to be displayed when somebody tries to access this web page without supplying the password or with supplying the wrong credentials. And this is the location of the file that contains the credentials, the .htpasswd file. It's located in /usr/share/www/html and .htpasswd. Okay, that is my second location. My third location is going to be the API, and this is where the reverse proxy functionality of nginx comes into play. Nginx by default is going to display anything that is inside /usr/share/www/html, whether they were HTML files, images, JavaScript files, CSS style sheets, anything. But as soon as the path starts to get the /API here, this means that we need this to pass to the backend application server. This needs to be passed to Node.js so that it can connect to the database and retrieve the results and get it back to us, or add whatever we pass into it via a post request, for example, to the database. So we need to instruct nginx to pass any request that has the /API/ to the backend server. This can be done using, let's first try files, URI or URI/. This means try first to find the URL if it exists on the web server. If we do have /API on the web server, of course we don't, but if we do, just have a look. Maybe this is a static file and we need to serve it to the client instead of going back to the backend server. If it doesn't, go to a variable that is called backend. This is where we are going to define our backend server. Location backend is going to be proxy pass to HTTP. This is just the IP address of the backend server, of Node.js server, or of the Node.js container. It will be 172.17.0. Again, 1. And the port is 3000. This is the port that we have agreed. That is going to be our Node.js port. Okay, so now we have the configuration file. Let's have a look at it quickly. It's going to listen to port 80. It's going to have a server name that is projects in docker.local. The root of the web files is going to be /usr/share/www/html. The index file, which is the default file that is going to be served to the client if no file was requested. Just the directory is gonna serve index.html by default. Then we are denying downloading or viewing any files that start with a dot. Of course, this is for the .ht passwd file, which contains the encrypted passwords of our files. We don't want this file to be visible to the clients. Then we are restricting access to a file that is called create.html. This file is used to create posts, so we need to restrict access to this file. We are going to use the .ht passwd file that we will create using the image, which contains the users and passwords hard-coded there. Then we are instructing Nginx to pass any requests that has /API to the backend server. And the backend server is defined here, which is the IP address of the node.js container. Okay, now everything is in place. Let's go to our terminal, ensure that we are inside the root of our web directory. Okay, now let's clear the screen and run docker build -t web. And let's use our build arguments, --build-org, password is pass123, so the user is Bob and the password is pass123, and this is going to be applied for any files in our current directory. Let's press enter and let it run. Okay, now the image has been built. If we now type docker image ls, now we have 6 images, 3 base images, Nginx, Mongo, and Node, and 3 images that we have built on top of them, DB, app, and web. Our application now is ready to start creating containers and testing it. That will be the starting topic of next lecture, so until then, take care. Alright, so now that we have our 3 images ready, we can now start creating containers out of them. We're gonna start with the database. So let's run docker container run --rm so that when the container is stopped, it is going to be automatically removed from the system. --name, let's call it db01. -d to be running in the background. -p 27017, this is the default port for MongoDB, so we are going to expose this port as it is. Not gonna make any changes to it, and this is gonna be based on our DB image, just like this. Okay, so now we have a container running, docker container ls. Okay, we have a DB, and it is running. Second, we need to run our application container, so docker container run --rm -name app01 -d to run in the background or in a detached mode. -p, it runs on 3000 by default. So let's also expose the port 3000 to our host, and it's going to be based on the app image. Okay, so now we have 2 containers running. Okay, now let's create the final container, which is the web server. So docker container run, again, --rm -name web01 -d -p. This time I'm going to give it port 8080 because we are running this on our using our non-privileged user, so we cannot start a web server on port 80. It's better to have a port that is above 1024, as we mentioned before, so we're gonna use port 8080 for that, and it's gonna be based on the web image. Okay, so now we have our 3 containers up and running. Let's open our browser and start testing our application. So if you type localhost 8080, okay, this is the blog that we have created. Of course, this is not the best blog you can find. You are free, of course, to do whatever modifications you want to this project and create further improvements. If we go here to create, and because we are instructing Nginx to use the authentication, we are going to be presented with this user and password prompt. Let's use the user Bob that we have hard-coded when we created the image. The password, if you remember, is pass123. Okay, now we are inside. We can create a blog post. Let's say, for example, hello Docker, subtitle, simple Docker post. Can add any content here. This is some content. Okay, and we press save. Post created successfully. If we go to home, you're gonna see that we have hello Docker, simple Docker post. If we click on it, you're going to see the title, the subtitle, the date, and this is some content about Docker. So this web server is talking to Node.js in the background. So if we open another tab and type localhost and we specify the port 3000/API/posts, we're gonna see that we have here a JSON output. This is title, hello Docker, simple Docker post, created date, subtitle, and content. This output is brought to you from Node.js. Okay, it is connecting to MongoDB. Node.js is connecting to MongoDB behind the scenes, grabbing this content, and AngularJS here is getting this content from Node.js. So if you want further proof, you can open the network tab of Firefox here, and let's refresh this page and notice this request here. Get posts, have a look here. It's getting it from localhost 8080/API/posts, and because this request has the API posts, if you remember from a previous lecture when we instructed Nginx to forward any request that has /API in it to the backend application server, so it connected to Node.js and grabbed this JSON output, as you can see. Of course, the IP address of Node.js is not going to be shown here because this all has been handled by Nginx. So that is the beauty of microservices architecture. Nginx is very fast and very efficient in serving static content. So content like this image, like the Bootstrap CSS framework that is used to create this look of the website, any JavaScript files that will help us create those effects, anything static is going to be served by Nginx, and it is very, very fast in this. It can be also used to cache content that is requested so that it is served faster. So let's have a look at this page, for example, about. Let's close this. Okay, about me. This is a static page. This does not have to connect to the backend application server. This is just HTML, some text, and some image. It does not need to go and make an expensive call to Node.js. But if you go here and if we want to have a look at this post, this has to go to the backend server. This has to fetch something from Node.js, and Node.js is going to take this ID, the post ID, go to MongoDB, and it's going to retrieve a post of that title from there. Let's have a look again at the API here. It's going to get this ID. It's going to ask for this ID at MongoDB, and the database is going to respond with this data, the contents, subtitle, and the title. Okay, so let's have a look at Nginx, and let's see what exactly happened when we created the .htpasswd file. So I can run docker container exec-it. The running container is web01, and let's execute /bin/bash against that container to have a shell inside it. So now we are inside. Let's go to /usr/share/www/html. Inside it we have, okay, of course, everything that we have copied from our local Docker host. But let's have a look at this .htpasswd file. .htpasswd file. It contains Bob as a user, and this is the encrypted password that I have instructed the image to create using the OpenSSL command. Let's have a look at our configuration file again, our Docker file for the web server. If you look here, this is the output of OpenSSL passwd-1 and the password. It's this string, and this is how Nginx is giving you the prompt to enter your user and password in here. Now, if I try to download this file, like for example, I was interested in getting /htpasswd, it's gonna give me forbidden. You are not allowed to download this file. That is because we have instructed Nginx to deny access to anything that starts with a dot. Now, one final thing before we leave this is I want to show you how and why we use microservices architecture. Now, if I stopped the app, for example, okay, let's use the full command docker container stop app 01. Now I stop this container, but the website is still working. Of course, it does not have any posts here, and if you go to create, you're not going to be able to create anything. If you just type here anything and press saved, nothing is going to be saved. But the website is partially working. It does not display, the page cannot be displayed or cannot connect to server or any of those
nasty error messages that are going to drive your visitors away. Of course, we can develop this further and make AngularJS display a message here that the application server is under maintenance, or we're gonna be back soon, or any other friendly message that is going to give a better user experience for your users. So that is the beauty of microservices. Every component is autonomous, it's atomic, it's isolated, it's working on its own. So even if I stopped the application server, the website is still running, although with partial functionality, but it is still running. Let's start that again. Docker container start app01. Okay, we have given the --rm, so you'll have to create that container again. Okay, now if we refresh this page, we're gonna have our posts again, and we can create whatever posts we want. That brings us to the end of this lecture. In the coming lecture, we are going to see some of the drawbacks of the architecture design that we have used, and we are going to address some of those drawbacks in this section. Other drawbacks are going to be addressed in later sections of this class. So until next lecture, take care. Right, hello and welcome back. Congratulations, we have now our application deployed using Docker, and we used the latest microservices-based architecture for that. However, the way we built our application has its own drawbacks. Some of them are going to be addressed in this section, some others are going to be addressed later. But before we go to the drawbacks of our architecture, let's address one question that might have popped in your head when we were deploying our application. Why we used the IP address that we used. When deploying our web server image, we said that it's going to talk to 172.17.0.1 at port 3000. That was the application server. And on the application server, when we wanted to instruct it to talk to the database, we ordered it to connect to 172.17.0.1 also. Of course, we are using here the MongoDB protocol, so by default it is going to connect to the MongoDB port, which is 27017, and it's going to work with a database that is called, or a schema that is called posts. But what is this magical IP address? What is so special about this IP address? This is the router for Docker. This is like the NAT IP address of Docker. If you have worked with NAT before, Network Address Translation, the NAT device has one external IP address, and behind these IP addresses are other private IP addresses that are not visible to the outside world. In order to access those IP addresses, the NAT device has to do something called port forwarding. So, for example, if I want to talk to the web server on port 80, I will have to go to port 8080. That is what we did when we created the container, when we passed in the -p, and we instructed Docker to pass in any requests that are coming at port 8080 to port 80. That is called port forwarding, and that is handled by the gateway or the router of Docker. This router is placed at 172.17.0.1 by default. This is a default IP addresses that comes with Docker when it is installed. So how to know which service I will need to connect to? Simply, you pass in the port of the service. So here we were using the port 27017. Here in Nginx, we used port 3000 to connect to the application server. So this is one way by letting containers talk to each other. Later on in this class, we're going to see other ways of communication between containers. Okay, back to our main topic of this lecture, the drawbacks of our architecture. First, MongoDB has no authentication. If you remember, when we connected to MongoDB, we did not pass any credentials. We did not pass a username or a password. If you are used to working with databases like Oracle or MySQL, for example, you know that every database and every schema must have a user, or at least there is the administrator of the database, of which we need to supply the credentials in order to be able to access the database. But with MongoDB, we just connected to it without passing any credentials. Of course, this is a major security flaw, and that is the default installation of MongoDB. It allows anybody to connect to it without using a user and a password, as long as the connection is coming from localhost. And of course, due to the architecture that we have just talked about, we are connecting to MongoDB as if the connection is coming from localhost, because it is behind a NAT device. So the connection is received by MongoDB as if it is coming from its own IP address, from its loopback IP address. So we were able to access it, and we were able to execute commands against it. But this needs to be fixed. The second thing is that the database data is stored inside the container itself. If the container is destroyed, the data is lost. So let's see that in action. Now we are on the terminal. Let's run docker container ls. we have now our database db01, and because we passed in the --rm when we created that container, if we type docker stop or docker container stop db01, it's going to be deleted. Now if we try to create that container again like this, and we go to the browser and refresh the page, you're gonna see that everything is gone. The post that we have created is no longer available. That is because we have destroyed the container and created it again. Doing so effectively deleted any data that was inside the container. So that is another drawback that needs to be addressed. Third, we had to hard code the IP addresses of the database and application servers we used. As I have just mentioned, we used the gateway IP address of Docker or the NAT IP address of Docker. That is not a good practice. There needs to be other ways for Docker containers to discover each other and to be able to connect to each other automatically without having to hard code their IP addresses inside configuration files. Next, the application server will fail to start if the database is not already running. So if I stop the database, the application is not going to run. That is because Node.js connects to the database automatically when it starts using Mongoose. So we need to find some way for Node.js to defer loading or to give an error message that the database is not yet up and running instead of just failing. The authentication mechanism is part of the image. We have hard-coded the username and the password inside the image itself. That is another security flaw, because anybody with access to the history of the image, like for example, if I type docker history web01, docker history web for the image, I'm gonna see the commands that were used to start this image, including the arguments that I have passed. So as you can see here, I have arg password equals pass. That was inside the file, and I also have password equals pass123, so I have both passwords, the default one and the one that I have entered during the image build. So this makes any user with access to the image have an idea about the password, which is a major security flaw. Finally, authentication is done over HTTP. Anybody who has access to the network and can sniff the data packets that are passing between your browser and the container will be able to effectively sniff the password because it will be sent in clear text. So this makes the whole point of authentication useless. You have to send the password over an encrypted medium, so you have to use secure HTTP or HTTPS for communication between your browser and the container. In this particular section, we are going to address just two of those drawbacks, which is the second and the fifth. So let's get to our terminal, clear the screen. Now, the second drawback stated that the database data is stored within the container. Docker has a method of letting you store the data of the container outside the container or on the Docker host itself. This is called volumes. Docker volumes are of two types. You can either store them automatically in some location managed by Docker. This is called named volumes, or you can specify your own path, your own file path for Docker to save whatever data you need from the container to that path. So in this particular case, we are going to use named paths. So the first thing we're going to do is that we are going to stop the container. So docker container stop db01. Okay, now all the data inside the container is lost. Now I'm going to run the same container, but with a slight modification. Let's just get to the command again. I'm just going to add here, right before the image, -v for volume. And I'm going to type db data. This is the name that I have chosen to the volume. Hence the name, named volumes. So db_data is the name of my volume, and it is going to mirror whatever is in /data/db. This tells Docker to map anything that is inside /data/db inside the container, which is the data that is stored by MongoDB, the location where MongoDB uses to store data. It's going to be saved in a named volume managed by Docker that I have chosen db_data for its name. Now, if I press enter, the container now is running. But notice here what happens when I type a command like this, docker volume db_data, or docker volume inspect db_data. Now you have an idea about the location, the physical location of this named volume on the system. It's in /var/lib/docker/volumes/db_data/_data. Okay, so now let's refresh the page and let's make a new post again, just to save the data. Title, persistent data. Subtitle, this data will
persist. Okay, so that is my post. Let's save it. Okay, let's start the app. It was not started. Okay, now let's save this post. Okay, let's go to home, ensure that this post exists. Okay, persistent data. Okay, now let's go to terminal and let's run docker container stop db01. Okay, now the container is stopped and it's also destroyed. So if I run docker container ls even -a, we only have app and web. DB is no longer available. We go to the browser and refresh the page here, just an empty page. If you go to the home page, there is nothing here because of course the database is down. Now let's start that container back, ensuring that the volume is mounted. The named volume is mounted. Okay, now it is running. If we refresh the page, okay, and we need to start the app because it fell into a problem when we tried to access the database and it is down. So let's start it. As you can see here, we have the post. The data will persist. This data will persist, and actually it did persist, although the container was destroyed and recreated again. So that is one way that Docker can save volumes on your host. Now let's have a look at our next drawback in this section, which is that the password was saved inside the image itself, and even when we used an argument that was passed during the build command, it was visible to anybody who could use the Docker history image. One way of working around this is keeping that file locally on our Docker host. So we are going to use Docker volumes for that, but we are going to use a local volume with a local path. We won't let Docker manage this path for us. We are going to specify it for ourselves. So the first thing we need to do is create a .htpassstability file locally on our system. To do this, we are going to run the same command that we have run before on our image, but this time it's going to be here. So user Bob, again, OpenSSL. Just want to make sure that OpenSSL is installed on my machine. Okay, it is installed. So printf Bob OpenSSL pass wd-1 pass 123. Let's change that to be my pass, for example, for a change, \n for a new line, and add this to a file on my home that is going to be called my htpasswd. Just a file. Okay, now if I cat my htpasswd, I find that we have a user Bob and the encrypted password, which is my pass. We need this file to be available for the volume when it starts. So let's go to docker container stop web01. Now it is stopped and deleted because we used the --rm during the container run command. Now let's run that again, but this time we're going to add -v as usual for the volume, and we are not going to use a named path. We're going to use home for the home, which is the tilde. If you are asking, the tilde here is for home. This automatically refers to the home directory of the current user. Same thing holds for $home. My htpasswd. As you can see here, it had bash automatically substituted the path for my home directory, then colon, and the location where I want this file to be mapped to, which is /us or /share /www/html. Of course, .htpasswd file. So now I'm effectively changing the htpasswd file that was created by the image with the one that I have created on my local machine. This one. So even if the user had access to the Docker history image command and was able to verify the password that was used inside the file, whether it was the default one or the one that was passed through the arguments, he or she will still not have access to the restricted part of the website because I have used a different htpasswd file. I've used a local one and mapped it to the remote one on the container. Let's press enter. Now go here, refresh the page, go to create. This is the cached version. If I refresh, I'm going to be presented with the authentication. If I type Bob and the old password, pass123. Okay, permission is denied, restricted content. If I type Bob and the password that I have just added, which is my pass, Now I have access to create new posts. That brings us to the end of this lecture and to the end of this section. This section we did a lot. We were able to create an application stack based on the latest microservices architecture. Using Docker containers, it was very, very easy to deploy this application. It was very easy to make changes to each and every component of the application. I hope you enjoyed this section and see you later. Hello everyone and welcome back. This is Ahmed again for Avionics, and this is the third section of our class, Projects in Docker. Now, in last section, we have successfully built the mean stack using a microservices-driven approach, and Docker helped us do this by creating lightweight containers for each component of our application. So we had a container for the web server, which is a client for the application container, which in turn is a client for the database container, and they are all working together to bring up the application for the clients. Now, what if you want to achieve high availability in this architecture? And in the same sense, what if you want to scale out this application so that it can accept more load or it can handle more requests? In a microservices-driven architecture, this is simply done by injecting more containers to the application. So instead of having one container for the web server, you might have 5 containers. Same thing goes for the application server, same thing goes for the database server. But a system like this needs something to manage it. So for example, if I have 5 containers all running the web server, which of those is going to accept requests and respond with the required data? Which of them is going to communicate with the application server and request the necessary dynamic data? The more important question is, what if one of those containers fails? Will the other containers know about this, so that requests are not routed to this failed container? Will some servers bring that container back to life, like restart it, for example? All those questions are addressed by what's called a container orchestration system. A container orchestration system has 2 main aspects when working with containers. The first one is that it treats your servers like herds of cattle, not pets. And I'm going to interchange the term server and containers a lot in this class. So when I say server, I actually mean a container, and when I say a container, I'm referring to the server. So what's the difference between managing your containers like a herd of cattle or managing your containers like pets? If you're having a pet like a dog, you care for it, name it, feed it, walk it, and nurse it when it gets sick till it gets back to normal. While if you are dealing with a herd of cattle, you don't bother to name each one of it or spend hours caring for each one. If a cow dies, for example, the rest of the herd is not affected. The same thing goes for containers. You don't name them like web server, reverse proxy, DNS, and so on. Instead, you might use names like www001 to www010. You have a large number of containers all serving the same application. And because containers are lightweight, as we mentioned in section 1 of this project, and because they consume much less resources than if you're running full virtual machines, you can have herds of containers, and you can bother less if one or more of those containers are down, as long as the others are working. The second aspect of orchestration systems is that it makes you describe your infrastructure instead of dictating it. Let's see the difference. In our blog application, we may write shell scripts to configure and launch the containers. If a script fails midway, the container does not launch. If the container crashes after launch, some other service must restart it. This is called an imperative system, where you issue commands and wait for the output. On the other hand, in the declarative system, you draw a picture of your infrastructure in the desired state. For example, you say it should contain 2 replicas of the database, 3 replicas of the application server, and 2 replicas of the front-end web servers. The system is responsible for keeping the infrastructure in this state. If one container is down, it will spawn another one. If too many containers are running, it will kill the extras. So this is one important difference between using a shell script or some programming language of your own to build and run containers and using an orchestration system. An orchestration system will ensure that you are always at the desired state and you don't care about the details. You don't care about how it is going to achieve this desired state. You just describe it, hand it to the orchestration system, and let it do the rest. There are a lot of existing orchestration systems like Docker Swarm, Kubernetes, and of course the cloud provider's own orchestration systems like Amazon ECS, Google Container Engine, Azure Container Service, among others. In this class, we are going to examine Docker Swarm as an orchestration system example. Docker Swarm comes pre-installed with Docker Engine version 1.12 or later. It enables you to achieve high availability for your application by creating a cluster of one or more Docker engines called a swarm. Before we start our implementation, let's get used to some important terminology so that you understand the topics that we are going to cover. When we say a node, we refer to the computer running Docker Engine. It doesn't matter whether it is on a physical machine, on a virtual machine, or on the cloud. A node may act as a manager node or a worker node. A manager node is responsible for the orchestration services. Think of it as the maestro, while a worker node is responsible for running tasks on the configured containers. A manager node by default is a worker node. However, you can configure it to work only as a manager node, but once you create a manager node, it automatically assumes the worker node role as well. A service is a collection of tasks that are going to run for a specific role. So for example, in our blog application, the web server is a service, the application server is a service, and the database server is a third service. So we're going to have three services in our architecture. Those three services are going to be orchestrated by the manager node, and we can optionally have another worker node to run the tasks against the services that we have, or we can use just one node to act as our manager and our worker node at the same time. And that is the architecture that we are going to follow in this lab. Now, that's enough for the introduction. In the coming lecture, we are going to start creating our Docker Swarm. So until then, take care. Right, so let's give the Docker Swarm a test drive. Let's see how it looks like. Let's see how I can create it and how it manages a container. So for the sake of demonstration, we are going just to create a simple service consisting of just one container. And it's going to run Node.js, but not the one that we are using in our lab example, not the one that we are using in the blog. We're just going to create a container running Node.js that will display hello world, and we're going to see how we can add this container to Docker Swarm. So we are now in the blog directory in our application. These are the images that we were using, my app, my DB, my web server. Let's create a new image. Let's call it Node Test. Let's get inside and let's create a Docker file inside this directory. So let's open our Sublime Text, create new file, call it Docker file. I've seen that before. I'm going to write it quickly. From node, which is of course the base image, run apt-get update-q, apt-get dist upgrade, apt-get clean, and apt-get auto clean. We're also going to expose port 3000 for this. Our app path is going to be also usr share, just a very similar Docker file to the one that we use in our Node.js application in the blog, except that it's not going to use all the features that we are adding to our Node.js application that is serving our blog. I'll copy everything to app path and finally, of course, cmd npm start. Okay, so that will be our Docker file. But of course, in order for this to work, we will need to also create a package.json and a server.js file. So let's create both of them quickly. Package.json. Our package.json file is going to be much shorter than the one we use in our lab. Say the application is called Node Test. The version is 0.0.1. Scripts, just give it the way, just inform npm about the way to start this service, which is node server.js. And that's it. Finally, let's create our server.js file. I'm going to just paste the code here, save it as server.js. Nothing is complicated here. It is just a very simple Node.js file, and it does not even use the express.js component. It just uses the plain Node.js functionality to start a simple web server that will only display hello world in an h2 tag. Okay, so now let's create an image out of this. So let's go to our terminal and let's use docker build -t node test in our current directory. Okay, we forgot -y here. Okay, let's go back. Okay, and now the image has been built. Now, the first thing we need to do in order to create a swarm or a Docker swarm is to initialize it. So in order to do that, we are going to issue the following command: docker swarm init. Okay, and now we have a very important message to have a look at. Swarm initialized, current node, and it's giving you the unique ID of that node is now manager. We have previously discussed the difference between the manager node and the worker node, and we mentioned that a manager node by default works as a worker node unless you specify otherwise. And it's informing you that in order to add a worker node to this swarm, you need to run the following command, of course, from another physical host or from another Docker engine. So from another Docker engine, if I want to add another Docker engine or another physical host to this cluster, I can run docker swarm join and give it the token that is uniquely identifiable for this node, and then the IP address of this node and this port 2377. I can also add a manager node to this swarm by running docker swarm join -token manager, and it's going to give you a set of instructions to follow. For the sake of this lab, we are going to use only one manager node, and it's going to work as a manager and a worker node at the same time. Okay, now in order to create a container and make that container be controlled by this swarm, we are not going to create a container, we are going to create a service. And remember from the last lecture, we said that we are going to deal with services when we are working with Docker Swarm or when we are dealing with orchestration systems in general. A service, as we mentioned, is a description of some role that you need to be available. So in our case, if we need a node test role or service, we are going to use the following command: docker service create. And you are going to notice a very interesting thing. You're going to notice that most of the options used with Docker service are exactly the same as the ones used with Docker container. So let's see. Docker service create is very similar to Docker container run. Let's say -d for detached mode, -- name for the name of the service. We're going to call it node 01, for example. Okay. -p 3000 for the port forwarding. And then you give it the name of the image, just like that, node test. Okay, now you have a new node that has been created with this unique ID. But take a note of this important message. Image node test latest could not be accessed on a registry to record its digest. Each node will access node test latest independently, possibly leading to different nodes running different versions of the image. What this message is trying to tell you is that the service registry happens to be inside that local host. So what is a service registry? The service registry is the component that informs the containers about which of them is up, which of them is down, which of them is available, and which of them is not. So when a container is up and running, it registers itself in the registry container and it declares that it is available. If a container is down, the service registry automatically detects that and removes it from its records. This is how high availability is done. This is how the orchestration system manages your containers like a herd of cattle, as we mentioned in the previous lecture. But if you have the service registry installed on the same physical host, this is going to be a problem because the other physical hosts will not be able to determine which containers are up and ready to have connections routed to them and which of them are not. So in this case, we need to have our service registry installed on a separate component that is available for all the physical hosts at the same time. Of course, in our lab, this is not the case because the service registry is bundled in Docker Swarm and it is installed on our physical node. So this is what this message is trying to tell you. This is just a warning. If you are running just one physical host, as in our case, this should not be a problem. Okay, so now if we run docker service ls, you're gonna see that we have one service running node 01. This is the name of the service. And have a look here. This is the number of replicas that this node is running. Replicas here means containers. How many containers is this service running? It's running only one container. So what if you want to add more containers to this service? Simply, I can use docker service scale node 01, which is the name of the service, equals like 3, for example. If I press enter, as you can see, in a few seconds, it is going to start and spawn new containers running the same service, and they are going to be available for you. Now, if I run docker service ls again, I'm going to see that now I have 3 replicas of my container. Now, let's see whether or not this container is running as expected, whether or not it is displaying the web page for me. So let's open our browser. Let's go to localhost 3000. As you can see here, I have hello world, which is the message that I instructed Node.js to display for me. Now let's clear the screen first, and let's run docker container ls. I have 3 containers, all running the same service. One of them is 4 minutes ago, which is the first one that we spawned, and 2 of them have been running since 1 minute ago. These are the ones that we used to scale out our system, to make our system run on 3 containers instead of 1. And notice here that all of them are listening on the same port, 3000. So how do they accept connections? How do they appear to me as if they are just one service? Now, if I'm accessing localhost at port 3000, no conflict is happening. One of those containers is serving me hello world. This is the role of the orchestration system. It has an internal load balancer that is going to route traffic among the containers that are running. Now, watch what happens if I did something like this, docker container stop, and let's pick one random container out of those, like let's say this one, for example, like this. Now quickly run container ls, we have 2. If I refresh this page, I'm gonna see that nothing is affected. I'm still having hello world. If I run docker container ls again, I'm gonna see that I have the container that I have just stopped. It has been spawned back to life. It has been recreated again for me, and that is also the role of the orchestration system. Docker Swarm has not only ensured that my service is not going to be affected when one of the containers is down, it also bounced that container back to life. It restarted that container. So I guess by now you see the importance of Docker Swarm and how it can achieve high availability for your application and also scalability easily enough in a very easy and efficient way. In the coming lecture, we are going to start to implement this approach on our main project, which is the Meanstack. We're going to use Docker Swarm to create a cluster for our blog application. So until next lecture, take care. Alright, in this lecture, we are going to implement Docker Swarm to our blog application in order to add more containers to our application. The first thing we're going to do is that we are going to get rid of the service that we have created in the previous lecture by using docker service rm node 01. This is the only way you can get rid of the containers that were created for you, because as you saw, otherwise any container that's stopped is going to be recreated again. But now you do not have any containers running. Great. Let's clear the screen. And in order to have your containers inside Docker Swarm with the configuration that we have already did, we will need to make some adjustments to this configuration. Let's see. So let's close this. We don't need node test for now. Let's have a look at my app, for example, and let's have a look at server.js. In here, and if you remember, we are hard coding the IP address of the router. If you remember from the previous section when we said that this IP address by default is used by Docker in what's called the bridged network. And in the bridged network mode, which is the default mode of Docker, it creates an interface on your Docker host or on the machine that is running the Docker engine. And this interface is always having this IP address 172.17.0.1. And this acts as a router or a NAT device. Underneath it runs the containers or runs the network that connects the containers with each other. But that is if you are running only one Docker host. You're not running a Docker Swarm, you don't have more than one Docker engine in your architecture. But in our case, we are going to need an isolated network for our containers to run in. That is because this network is going to be used by Docker Swarm not only for the internal communication of the containers, but also if you want to add more than one Docker host to your Swarm. So in an isolated network, we are not going to use this IP address because it's not going to be available. So how are we going to address our containers? How are we going to communicate with our containers? Simple enough, we're going to give them names. So for example, the database is going to be called db_server. That is a name that I have chosen. And later on, I will tell you where this name comes from or where it can be added. Okay, so that is the database server. Let's have a look at our web server, and in our configuration file, which happened to be in /etc/nginx conf.d main.conf. And here we used to have, again, 172.17.0.1. I'm going to change this to be app_server. Again, this is a name that I have chosen, and in a few seconds I'm going to show you where this name is going to be configured. Okay, so now that we have made those changes, we are going to need to build our app and our web server again, because we have made changes to our Docker file. So docker build-t my app, and let's go to my web server and do the same thing. Just change my app to be y web server for the name of the image. Okay, now we have our images built and ready to start spawning services out of them. But before we do that, we need to create the network that I have just told you about. The network, the isolated network that will be used by Docker Swarm for the containers to connect through. So docker network create -- driver overlay. This is the type of network that we're going to create, and we can give it a name. I'm going to give it the name of blog_network. Okay, it has been created. If you type docker network ls, you're going to see that we have now blog network. And notice here the scope. The scope is Swarm. This means that this network is going to be used by our Swarm orchestration system. And this is the bridge network. This is the default network that Docker uses if you don't specify a network when you start running containers. This is the bridge network, and this is the one that is having the IP address that we used as our router. But in this lab, we're not going to use this bridge network, so we're not going to use the router address. We're going to use some other way of communication, which we are going to see right in a second. So let's start creating our services, and let's start by our database. So docker service create -d for detached mode -- replicas, and this is a new option here. It specifies the number of replicas that you need for your service. So instead of creating just one replica or not using this option and then using Docker service scale, you can just specify here that you want the number of replicas for this service. In this specific lab, we're not going to use more than one replica for the database. Now give it a name, db_server. Now this is the name that the application server or that Node.js is going to use to connect to the database server. Its service name, db_server. All the containers that are going to be run under this service are going to bear that name, db_server, and the application server is going to be able to communicate with the database using this name. I'm going to prove that to you before we start the application. Now, one new option that we're going to see here is the network. This specifies the name of the network that you want this service to be connected to. So of course, it's going to be our overlay network that we have just created and named blog_network. Then we're going to use the named volumes to keep data persistent. Type is volume, source database_volume. This will be the name of the named volume. Remember from the previous section, we said that named volumes are managed by Docker. The destination is going to be /data/db on the container itself. Of course, this applies to as many containers as you are going to create in this service. However, in our specific case, we are creating only one replica of this service. Okay, press enter. Okay, and again, the message that will always be displayed as long as you don't have a separate component of your service registry. And if you run docker service ls, you're gonna see that, okay, it's running and it is having one replica. Let's now create our application. Similarly, docker service create -d for detached --name app_server. And again, this is the name that the web server is going to use to communicate with any container under this service that is handling the application server role. --replicas. I'm gonna create 3 replicas for this. --network. Of course, our blog _network. And this is going to be based on my app image. Okay, and running docker service ls. Okay, notice here that it's still starting. Replica 0 of 3. Now it is all started. Replicas 3 of 3. Now the 3 replicas are started. If we run docker container ls, now we're going to see that we have 3 replicas or 3 containers running our node.js application and 1 running our database. Now before we go to our final service, which is the web server, I want to show you something. Let's go to docker container exec and let's choose one of the containers that are under the application server or the app server service, and let's run bin bash. Now we are inside one of our node.js containers. If I try to ping db_server, I'm going to receive a reply. And I'm going to receive a reply from some internal IP address. I'm not interested in this IP address. I'm interested in the fact that I was able to use the name db_server, and it got me a reply. And this reply, I'm sure that it is coming from the database service. So how did Docker, or how did this container know that db_server was referring to this container? That is because it simply used a DNS server. The DNS server that Docker Swarm uses is this one, nameserver 127.0.0.11. This is the DNS server that Docker Swarm is using to enable the containers or the services to talk to each other by their names. And this name is the one that I specified when I specified --name and I gave it the name of the service. Okay, so let's exit. And I needed you to have this information and take a very good note of this, because we are going to use it when we configure our Nginx service. Now, why do we want to configure our Nginx service? That is because Nginx has an important issue when it deals with DNS requests, and that issue is going to affect us when we use Nginx containers in Docker Swarm. That issue is simply that Nginx tends to cache DNS responses. So let's say, for example, that Nginx is trying to resolve the IP address of a server that is called app_server, which is, of course, our node.js service, and it received a reply similar to this one. The DNS responded with an IP address like 10.0.0.4, for example. Now, this IP address is going to be cached inside Nginx. That is because, of course, this helps to boost performance, but when you are dealing with microservices, when you are dealing with containers, these IP addresses tend to change every once in a while. That is because the container might be moved via the Docker Swarm or the orchestration system, whatever orchestration system you're using, from one host to another, for example, and this IP address might change. So if that changed, Nginx will still use the old one, and of course this might have adverse effects on the application as a whole. So for that reason, we will need to inform Nginx that it is going to use this IP address as the DNS server, and it is going to cache the replies coming from this server only for 10 seconds. So let's go to our configuration file of Nginx again, and under index here in the same stanza at the server, I'm going to add resolver. This is Nginx syntax 127.0.0.11. IPv6 is off in order to prevent unnecessary IPv6 requests, and then valid equals 10s or 10 seconds. This means that it's going to cache the request or the response for only 10 seconds, and that is all what I need in this configuration file. Now, if I go back to our terminal here, I may need to run docker build on -t my web server again, because I made a change to the configuration file. Okay, and now I can create the final service in my architecture. So docker service create -d --name web server --network blog _ network --replicas 3. And notice here that this is the only one where I forwarded ports. In the previous services, I did not care to forward ports because I do not need to expose any ports except from that final service in my architecture. So I'm gonna forward port 8080 on my local Docker host to port 80 on the container where Nginx is listening. And then give it the name of the image, which is my web server. Okay, now the service has been created. If I type docker service ls, okay, now I have all my services up and running, with the last one only exposing port 8080. Now if I go to the browser and I switch it to localhost 8080, I'm gonna find that I'm inside projects in Docker blog that we have seen in the previous section. If I go to create, and I didn't care here to specify an external .htpasswd file, I'm gonna just use the defaults, user and pass. Let's create a title, hello from the swarm, subtitle, first one post. Okay, let's save. Okay, go to home. Okay, now you can see that it is running. Posts are showing and I can access them, so the database is accessible. Now if I go to docker container ls, and I can use docker container kill even, which is a new subcommand that we haven't tackled before. It's gonna just, as the name suggests, it's going to kill the container instead of stopping it, which is exactly what happens in real world environments. The container might just crash. So I'm gonna kill one of my web servers like this. This is the correct ID. Okay. If I refresh the page, you notice that nothing happened. Nothing has been affected. And if I run containerless, I'm gonna see that again I have 3 containers running Nginx, which with the last one created only 2 seconds ago, which means that Docker Swarm has quickly respawned the failing container. And that is how, as we mentioned, you are describing your infrastructure and you are giving it to the orchestration system, and you are handling it the responsibility of retaining that state. If a container is down, it's going to be respawned, and at the same time the service is not going to be disrupted. Now that brings us to the end of this lecture. In the coming lecture we are going to see one extra component of Docker Swarm that is going to even automate the whole process by using a configuration file. So until next lecture, take care. Alright, in this section we had a brief introduction to orchestration systems in general, and we had a close look at Docker Swarm, which is the default orchestration system that comes pre-installed with Docker. You don't need a separate installation for Docker Swarm. It ships with Docker, and it contains its own service registry and its own load balancer. All this is in the same package as Docker. Now, Docker Swarm has an extra component that we need to have a look at, which is called Docker Stack. Docker Stack is used to automate even creating a Docker Swarm. This is very useful if you want to automate Swarm creation using a configuration file. So let's have a look at this component. Let's clear the screen. And Docker Stack uses a configuration file that is written in the YAML language. YAML language is it's not a language actually, it's a data serialization format, just like JSON, but of course it has a different standard, and it is used by many applications, mostly Python. It is very easy. I'm gonna have a look at it quickly. First, let's ensure that we are in the root of our directory, and let's create a file. Let's call it blog_swarm.yml. Okay, you're gonna see that it's very easy, very straightforward. Even if you haven't written any YAML before, you're gonna see that it follows common sense. So first is version 3. That is a header. That is a common header. Then you start specifying the services that you need this swarm to contain. So we have services. First service, if you remember, was called the DB server. The DB server is based on an image that is called MyDB. It will use a network or networks. And networks here, since it is plural, this means that it is going to be a list, and lists in YAML start with a dash followed by a space. And pay a lot of attention to indentation in YAML. YAML works by indentation, so this space here at the start of the line is very important. Lines with the same indentation means that they belong to the same scope, and this is very important in YAML. If you mistyped an indentation, you will destroy the format of the whole file. So I advise you to use a programming text editor like Sublime Text or Notepad++ or any code editor of your choice so that it may preserve indentation for you. Okay, so networks, we are going to use our blog network, and then in order to deploy it, we will need replicas of 1, and the restart policy is going to be on the following condition, which is on failure. The database server is also going to use volumes, named volumes, and our only volume here is going to be database_volume. This is the name of the named volume, database volume. And notice here that I did not add a space between database volume and the path for the database, for the file system that contains the data on the container itself. That is because the colon in YAML is a special character. As you can see here, all my identification is followed by a colon, then a space, then the value. The key, then a colon, without a space, then a space, then the value. But here I'm not using this colon as a separator. I want this whole thing to be a string. Volumes is going to be this one as a whole. This is not a key and a value. I want it to be used like this: database_volume :/data/db. So make sure that you do not add any space between the name of the volume and the path of the volume. This is the only exception here. For the rest of the file, please add a space between the name and the value to indicate for YAML that you mean a name and a value pair. Okay, so that was for the volumes. Now let's have a look at, now let's start writing our app server. Our app server is going to be based on the image that is called my app. It's going to use the networks, that is blog network. And notice here that we're going to add a new statement that wasn't added before. Depends on. This means you'll need to start whatever comes in depends on before you start this service or before you create the service. So it depends on db_server, which we already defined previously. Okay, deploy condition on failure. Finally, the web server. Again, the image is my web server. The networks is going to be blog network. But here we are using port forwarding, so I'm gonna add ports 8080 forward to 80, and depends on app server must be running first before the web server is created. Deploy replicas 3, restart policy condition on failure. Okay, so that was our services. Now let's have a look at the extra components that we need to create. Just make sure that we are on the same indentation level as services. So we're going to create services, we're going to create networks. For this to work, we need our, of course, blog network, followed by a column like this. And volumes, we need our database volume and a column. That is our YAML file. Save it. Now let's use docker stack deploy -c and then give it the path to the file. We create that file in the same directory. So we just give it the name of the file like this. And before we create the services, we need to remove the ones that we already have. So we have here 3 services running. Let's remove them quickly one by one. So docker service rm web server, docker service rm app server, docker service rm db_server. So now if we run docker service ls, we don't have any services running. Now let's clear the screen. Now docker stack, this time, deploy -c and then the path to your YAML file. So our YAML file was called blog_swarm.yml, and then the name of your stack. This is very important. This is the name by which Docker stack is going to refer to this specific instance or this specific stack of your application. So I'm going to call it blog_swarm. Press enter. Okay, and seems that we have a mistake in our YAML file. Let's have a look quickly. Okay, as you can see, this was not indented properly. Should be the same indentation level as deploy and image. And I hope you see by now the importance of indentation in YAML files. Just a small indentation here corrupted the file and produced that error. Now let's repeat the command again. Okay, now it's creating the network, the service, app server, web server, and DB server. Now if I type docker service ls, notice that it is still spawning them. In a few seconds they will be all complete. Now they are all running. All the replicas are running. If I go to my browser and if I go to home, create, for example, another post, docker stack post. Okay, I'm safe. Go to home, and as you can see, the blog is working the way it should without any problems. And if I run docker container ls, I'm gonna see that I have 7 containers running, as I described how my infrastructure should be like. So that brings us to the end of this lecture and to the end of this section. I hope by now you have a clear understanding of what container orchestration systems are, and you had a brief introduction to Docker Swarm. So until next section, take care. Hello everyone and welcome back. This is a new section in your class, Projects in Docker by Aryonics. My name is Ahmed, and in this section we are going to add resiliency to our blog application. Now in the previous section we created our blog application using a microservices driven approach. We created several containers for each of our application layers. We created containers for the web server layer, for the application layer, and for the database layer. However, we had a serious drawback in this architecture, which is that all of our containers were physically located on the same machine, on the same Docker host. This means that if this Docker is down for any reason, and machines do go down from time to time, we have a serious problem because all of our containers will lose their Docker host. Now, having more than one container per layer of the application is beneficial and it will provide high availability for you. But if the Docker that holds these containers is down, this is not going to save you. Your whole application is going to be down. So in this section, we are going to learn how we can scatter those containers on more than one Docker host, and also how to manage how those containers can be moved from one node to another, and how storage is managed by Docker in general, and how we can create shared storage so we do not have to worry if a container was moved from one node to another, that its storage will always be available to it. So let's get started. Now for the purposes of this lab, I have created 5 virtual machines to mimic a real-world example. So I have one machine for the manager 1, another machine will act as the second manager, so we'll have 2 manager machines or 2 manager nodes. I also have a worker machine, 2 worker machines actually, worker 01 and worker 02. And finally, I have a service registry machine. I created a 5th machine called SR01. This is going to hold my service registry component. Now, remember in the previous section when we were creating our services, we had an important warning from Docker that our swarm does not contain a dedicated service registry component. This means that if we have more than one Docker host in our cluster, those hosts will not have an idea about the images that we are using. Now, in order to avoid this and in order to ensure that all our nodes are going to use the same images that are used by the other nodes in the same swarm, we have to create a private registry, or we have to use a shared registry of some type between all those nodes. So I have created this machine and I'm going to use it to create a private service registry that is going to be used by all the nodes of our swarm. So let's get started. And the first thing we need to do is to start login to each of our machines so that we have an easier way to manage them. The first machine is the manager. It has having this IP address 192.168.100.100 to the password. Okay, this is manager 01. Let's open another tab in our terminal and log in to the second machine of our swarm. The swarm is not created yet. Those are just virtual machines that I have created and installed Docker on each of them. I haven't created any swarm yet. We're going to create that together in a moment. Now let's log into our first worker machine having the IP of 192.168.100.10 and our second worker machine 192.168.100.20 and finally our service registry machine. Okay, now we have our 5 machines on the terminal. Let's start by creating the swarm. So docker swarm init. All of this had been covered before in the previous section, so consider this just a quick recap. The only difference is that we are going to do this on more than one node. So docker swarm init, and because we have more than one IP address on our machine, we will need to specify the address with --advertise -eddr, and I'm going to use the one that is shared with my host, which is this one. Okay, now we have initialized the current node, and this is the manager. I'm going to use this command in order to add the second manager. So it's docker swarm join -token manager. All what this command is going to do is that it's going to give me the command that I must use on my second manager in order to join this swarm. So let's paste it here. And now, okay, this node joined the swarm as a manager. If I type docker node ls, I'm going to see that I have now 2 managers. I have the leader and I have a secondary one. Both of them are ready. Okay, that's nice. Now I can copy the command that is going to be used to add workers. And I'm going to add it to worker 1, worker 2, and my service registry machine, the one that I created for our service registry component. Okay, now if I go to any of my managers and I type docker node ls, I'm going to see that I have now several machines. 2 of them are managers and the other 3 are workers. Okay, now let's move on to create our service manager. Docker provides an image that can be used to create a service registry. It's very easy actually to create a service registry. You can either create a container. Let's go to the machine. Let's clear the screen. So you have 2 options, either to use a container or to use a service. But in our case, we need to use a service because we are using a Docker swarm. So Docker swarm is going to need this service to be part of the swarm in order to be able to connect to it. So in order to do that, I'm going to use a command that will create a service for us. But when I finish, I'm going to show you the same command that can be used to create a container, so that if you want to create a private registry that is not part of a swarm, just to test out things or create your own lab, you have an idea about this command. So first I will need to create the swarm network. So docker network create --driver overlay. Remember from the previous section, this is needed for our swarm to use this network. I'm gonna call it blog_network. Okay, it has been created. So let's create our service, docker service create -d -p 5000. This is the port that the service component is exposing. This is the port that we need to be public, and this is the port that is used internally by the component or by the container. I'm going to use an image that is called registry2, and of course I will need the network to be the network I just created, which is the blog network. Okay, now I can press enter and the service will be created. However, this service is going to be created on an arbitrary node. It's going to be created either on manager 1, 2, worker 1, 2, or on the service registry node that I have created. But I want this service to have a static IP. I do not want the IP address of this service to change, because if this service is moved from one Docker host to another, the IP address is going to be changed, and it's going to be having the IP address of the Docker host on which it is currently running. And of course, I don't want this. I don't want this to happen. I want this service to be always bearing the same IP address. So in other words, I need to constrain this service to be running only on one Docker host. And this naturally is the Docker host that I've created specifically for that, which is SR01. I want it to be bound to this Docker host, and I don't want it to move to any other host. So in order to do this, I will add a new option that we haven't seen before, but it's very powerful. It's called constraint. Constraint, as the name suggests, is going to add constraints to your service. The constraint I want to add is the node.id. I need the node ID to equal to the node ID of SR01. And where can I get this? Okay, that's simple. I can always run docker node ls. I'm gonna get the ID of the node from here and go here and paste it. Now I have my constraint added. So this service is always going to be bound to the node with the ID of the SR01. And you might want to add a name for this service. Let's type --name registry like this. And let's press enter. Okay, and now we have the service created. If I type docker service ls, I'm gonna see that now I have service registry running. And notice that it is still not running yet, still having no replicas. That is because the image is still being pulled from the Docker Hub, Docker registry. So I can run docker ps registry. Okay, it's still preparing. Okay, and now we have service registry successfully installed. And notice that it is running one replica as we instructed it to. And if we run docker service ps registry, I'm gonna find that it is running on the node SR01 as we instructed it to. It will not move from this node to any other node. This will ensure that we can always reach our service registry by going to 192.168.100.30 at port 5000. Now that brings us to the end of this lecture. In the coming lecture, we are going to start tagging our images so that they are available through our service registry, so that they can be provisioned to any node in the swarm that requests them. So until next lecture, take care. Alright, hello everyone and welcome back. In the previous lecture, we have successfully created the service registry that we are going to use in our swarm, and we created that on one of our Docker nodes, and we instructed the service not to be moved from this node so that it has one and only one IP address that we can reach it at port 5000. Now, before I go on, I will need to highlight one important fact. This port is the non-secure port of Docker service registry. So if you are going to use this in a production environment, and if you want to create a secure port, you will have to use a certificate. And a certificate is signed from a certificate authority. So you should have a key for your TLS connection and a certificate. Once you have both of them, I'm going to show you the command that you should use to create a secure service registry. This is just for demonstration. I'm not gonna use this command because I do not have a certificate. And even if I use a self-signed certificate, Docker will not accept it. Docker needs a certificate that is signed from a certificate authority in order to work on TLS. So the command is as follows. I'm gonna create a container that uses TLS. Docker 1-d --restart always. You can give it a name, registry, can give it a volume, and this is assuming that you have a directory on your current working directory that is called certs, where you will have your certificate and your key. It's going to be mapped inside the container to a directory that is called certs on the root. And then I'm gonna add some environment variables that are needed for this to work. So registry_http is 0.0.0.0.443, which is the default port anyway. -e registry_http_TLS_certificate is /certs, which is the directory that should contain your certificate and your key file. This is the file for the certificate, domain.crt. I'm assuming that this is the you should replace this with your own certificate file. And finally, registry_http_TLS underscore key is slash search domain.key. This is supposed to be your key. You should replace it with your own key. Then finally, you will map the 443 port with the 443 external port. You're going to map the ports as you do with any container, and then the name of the image, which is registry2. So this is the command that you should use if you have a certificate that is signed from a certificate authority if you want to enable TLS when working with Docker Service Registry, and I strongly recommend that you do that if you are working in a production environment with your private service registry. A valid alternative also is to use a third-party service registry that is hosted on the cloud, and they will handle the TLS, they will handle all the technical details, and you will have a service registry that can be used and shared among your Docker engines or Docker nodes. So, since we are going to use a non-secure port for the purposes of this demonstration, you will need to make some changes to how Docker connects to the service registry. So I'm going to use sudo, and I'm going to edit two files. So in /etc/docker, and a file that is called daemon.json. If that file does not exist, you will have to create it. And you're gonna need to add the following. It's JSON format, insecure registries, and you give it an array of the insecure registries that you are going to use. In our case, it's only one, which is 192.168.100.30. And of course the port is 5000. Close and close. Okay, let's have a copy of this line to add it in other nodes. I'm gonna add it quickly. Okay, now the second file that we need to change is /etc/default/docker, and this file already exists. We are going to add the following: docker underscore opts or options equal -- insecure registry, and then you give the IP address of your service registry, just like that. Let's again take a copy of this line to add it to the rest of our nodes. Okay, once I did that, I will need to restart the Docker daemon on all the nodes as follows: systemctl restart Docker. Okay, now once done, we will need to create tags for our images. And if you remember from a previous section in this class, we mentioned that the image name may include its repository, the registry where it is saved, and optionally a username and a password that will be used to log into this registry and download or pull the image, along with any tags that this image may have. We need to configure our images so that they reside in our newly created service registry instead of the default. So in order to do this, I'm going to get inside our directory where we have our blog application, and I'm going to go to each and every one of them, and I can either tag the image or build it all together. I'll prefer to build it. I'm going to build the image, give it a tag 192.168.100.30, which is the IP address of our service registry with the port this is needed, then the name of my image and a dot. Now, if you want to add any tags, they can be added as you know by adding a colon and the tag name. But this is not the tag. This is the repository where I am configuring this image to be residing at. Whenever I want to call this image, Docker will automatically infer that it is located on this service registry at this port. Press enter. Okay, now let's go to our second one, which is my app. Issue the same command. Just change the image name to be my app. And finally, the web server. Okay, now let's clear the screen, and if I run docker image ls, I'm going to see that now I have my images, but they have the service repository attached to them or prepended to them. You're going to see the significance of this new image name in a moment if I run docker push and then I give it the name of my image like this. Notice that this is going to be the name of our image from now on. Whenever you want to refer to MyDB, we'll have to prepend this IP address with this port to the image. If I run docker push, notice what happens. It is going to push this image to our newly created repository. It's going to push it to our container that has the registry, the SR one, this one. Why? Because I have prepended the image name with the IP address and the port of the service registry component. Docker push is a new command that we haven't seen before. It just pushes your image to a service registry. If you have an account on Docker Hub and you want to create your own images and push them there, you can use the Docker login to log in with your credentials and Docker push to push your image to the registry. Okay, now I have pushed the first image. I need to push the second and the third. So my app. And finally, my web server. Okay, so now I have all my images pushed. Just clear the screen. And now let's see what happens if I try to create a service manually and create several components out of the service to be spawned or to be scattered across my Docker nodes. And also they are going to use our newly created service registry. So let's start with the database, docker service create -- name db_server, and this is going to be based on 192.168.130:5000/mydb. Now let's hear that I am referring to the image using its repository name, and this is going to be my only way of referring to the image from now on in this swarm. I have to add the IP address and the port, then the database itself. And of course, we will need to add the network, -- network, log_network. Press enter. And notice first that we do not have the warning that used to appear before when it told us that we do not have a service registry and that images do not have a central repository or a central registry where they are going to be verified against. Now we have our central repository or a central service registry on the SR01 machine. Now if I run docker service ls, I'm gonna see that, okay, I have two services, the registry service and DB server. And DB server, if you are curious, is hosted on manager01. It has been hosted on the first Docker host. Now I can also start creating the rest of my application. Docker service create, let this be -d this time, so to be less verbose, -- name app_server -- network log_network, and the image again my app. Let's give it a larger number of replicas than before. -- replicas equal, let's say 7. We'll have 7 replicas for this one. Okay, docker service ls. This is still being launched. Okay, and now we have 7 out of 7 running. Let's add our web server, docker service create -- name web server -d -p 8080 to 80 -network log network -- replicas Let this be 9. Let's say that our web server needs to have higher replicas. And of course, it's based on 192.168.130:5000 / my web server image. Okay, Docker service ls. Okay, in a matter of seconds, all of our replicas are up and running. Now, let's go to the browser and let's start by typing one of the IP addresses that we have, 192.168.100.100.8080. Okay, projects in Docker. Let's change the IP address to be the one of the second manager. Still, we have the application, one of the nodes, one of the workers, first one, second one, and the third one. If you try the database, first post from, let's say, second post from Swarm, using service registry. Okay, let's save. And if you go home, you're gonna see that our post appearing on the front page. It's working. This means that the database is also working successfully. Now, you can add a load balancer over the top of those IP addresses. Notice that all of them are displaying the same server, the same page with the same content from the database. You can add a load balancer over those physical hosts, and now you have a really highly available Docker blog application. Now, if you want to do the same thing using Docker Stack, all we have to do is go here, and you'll have just to change the name of the image, and instead of MyDB, my app, and my web server, just add the IP address of the service registry, just like this, 192.168.130:5000 / the image name. You're going to do this on all of the images in the YAML file, and it's going to work equally. Actually, you are going to see that later when we use this file to manage the shared storage later in this class. But for now, you can just see that using a private service registry and using several Docker hosts, we were able to add some resiliency to our blog application. Now, if one of those is down, let's say, for example, let's take down one of the workers, for example. Let's say worker 1 sudo power off. Just like that. Okay, now the machine is powered off. However, if we go back here and we refresh the page, I'm gonna see that it's still working. Of course, the IP address of the worker 1 will not work if we try, but the rest of the IP addresses are working, and they are connecting to the database successfully without any problems. Now, what happened is that, let's go to one of the managers, Docker service PS web server, for example. As you can see, some of the nodes or some of the containers are shut down. That is because worker 01 is shut down. So any containers that was distributed or that was assigned to worker 01 are now shifted to other Docker nodes. Once this worker 01 node is up and running again, it will have its own share of containers again. So let's do that. Let's go to worker 01 that was shut down, and let's start it again. Okay, it's started. Let's get back here and v1 service PS web server again. You're gonna see that it is accepting connections now, although maybe it's not receiving its share of containers yet, but it is serving the application. The IP address is now working. This is the IP address of worker 1, and it is serving the application equally as the other workers in the swarm. So that brings us to the end of this lecture. In the coming lecture, we are going to discuss how Docker manages storage in some more detail, and we're also going to address another flaw of our application, which is that containers are tightly coupled with their storage. If the database container is shut down or removed from the swarm and recreated, we lose the data. If we created an external volume for the database, it is going to be tightly coupled with the Docker node on which this storage is located. So we are going to need to address this drawback in the rest of this section. So until next lecture, take care. Right, hello everyone and welcome back. Now that we have added a layer of resilience to our blog application, we still have an unaddressed issue as we mentioned in the previous lecture, which is the database permanent storage. When we used to run the swarm on a single node, that was not a problem because the mounted volume was residing on the same node as all other containers of the swarm. So, we're sure that the container will always have access to its data because everything is running on the same machine. But now that we are running our containers on multiple nodes, it is possible that the database container is moved from one node to the other. We need to ensure that the container will still have access to its storage or the database will not work as expected. Let's first discuss how Docker manages storage before we delve into the different ways by which we can keep external storage available to the container. In order to understand Docker storage, we need to first have a brief look at Docker's way of handling images and container file systems. Docker tries to keep resource consumption at the minimum. Storage is no exception. For that reason, it uses a file system type called Union File System. So how does Union File System work? The typical file system stores files and directories on the disk. If a file is deleted, renamed, or has its contents changed, there are no other versions of it. If a new file or directory is added to the file system, the contents of the file system changes forever. In a UFS or a Union File System, the case is different. The file system is treated in the form of immutable layers. Each layer is stacked above the other. Each layer may have a different set of files and directories, but the system presents this stack of layers to the user as if it was one contiguous file system. However, when changes are made to the content of the file system, the outermost layer is the only one that gets affected. Any layer underneath it is always read-only. But what if the file that you want to modify is located on one of those inner layers? In this case, the file is copied to the outermost layer, modified and saved there, masking or shadowing the original file. This process is referred to as copy on write, or COW in short. This way, there might be several versions of the same file scattered around the layers. But as the end user, you will only see one contiguous file system. If a file has several versions, the only version that you can see and interact with is the one in the outermost layer. Docker uses the overlay FS, which is one of several drivers used for implementing UFS. But why does Docker use UFS, or why does it use Union File Systems anyway? Why it doesn't just use the normal file system as any other Linux file system or even Windows? In order to understand the reason, let's say that we are using an Ubuntu image to build a web server. The process is done as follows. The Ubuntu image is pulled with all its underlying layers from Docker Hub or from whatever source you are pulling the image from. Then, when you run docker build, a new layer is created according to each change you do to the image. So, for example, apt-get install Apache will create a new layer with all the binary and configuration files Apache needs. Now, let's say that we need to use this image for another project, like Node.js for example. If the Ubuntu image was modified by the changes done to install Apache, Docker will need to pull a new, clean Ubuntu image to be used with the new project. This consumes more space and also wastes time. Now imagine what happens if you want to build a dozen projects, each is based on Ubuntu. This is going to be a lot to download and a lot of space and time wasted. But using the UFS, the same Ubuntu image can be shared among as many images as you need. The only layer you'll be making changes to is the outermost layer. You will only consume the extra space needed to install the application itself. Now what happens when you create a container out of the image? A container gains a read-only access to all the layers except the outermost one. Because of this, data is not retained when the container is removed from the system, because the only data that is available when you create a new container is the data enclosed in the image. Because of that, we used volumes to make data persistent when we used MongoDB. Also when we wanted to preserve the .ht passability file outside of the web server container. So now that we know the theory, let's see the different ways by which we can store data outside the container. Most of what we will cover here have already been covered before when we were deploying our blog application and later when we used Docker Swarm for high availability. So you can consider this as a quick recap. You might have noticed that we used the -- mount option when we created the database service. If you remember, the database service was created as follows. Docker service create -- name db_server -- mount. Then we use something like this: source equals database volume and target equals /data/db. And then the rest of the command, if you remember. -- mount is the new syntax that Docker is using to define volumes instead of using -v or -- volume, which are still valid, but they are going to be deprecated soon. So make sure, of course, this was source, I'm sorry, source equals database volume and target is data_db. So this is the new syntax as we just mentioned, but the old one is still available. You can use it, which was like this: -v, and then you give it the source database_volume, then the destination like this, just /data/db. But the newer syntax is more verbose and it provides a clearer view for the user, so you are encouraged to use the new syntax. Now, in this particular example, we are using a named volume. As we mentioned before, a named volume is a volume that is managed by Docker, and you do not get to specify the source directory in which the files are going to be saved. This is managed fully by Docker using a storage driver of its own. And if you want to, you can use Docker volume to manage named volumes as you wish. So Docker volume ls, for example, is going to give you the available volumes that you have in your system. This is the driver that Docker uses to access the volume, and the local driver is the one that ships with Docker in the default installation. You can also use Docker volume inspect to see what this volume actually has. So this volume, as you can see here, is mounted on this mount point. You can take a copy and have a look. This is the local mount point. Currently does not have any files. Probably this was created for one of our MongoDB containers. Okay, you can also use Docker volume to create a new volume of your own. So I can use Docker volume create and then give it the name of the volume. I can also specify options like the driver I'm going to use, whether or not this volume might reside on a remote machine. For example, as we are going to see later in this section, we are going to create a remote volume on an NFS share. So Docker volume is our friend here. It's going to help us create this volume using its driver, and then we can just refer to this volume by name to mount whatever storage we need from the container to this volume. So again, bind volumes are the ones that are managed by yourself. They are tightly coupled to the Docker host on which the service or the container is created, while the named volume is the one that is managed by Docker, and it does not need to necessarily reside on the same Docker host where the container or the service is created. But the problem with named volumes is that they do not get removed when the container is stopped or deleted. So I might have Docker, again, Docker volume ls. Those volumes may not be used anymore, however, they still exist on my machine. So a quick command to clean up any possibly wasted storage by Docker volumes that are no longer used is to use Docker volume prune, like this. Yes. Okay. And if I did have any volumes that are not used by containers or services on my system, they are going to be deleted. So make sure you run Docker volume prune every now and then when you find that you are running out of space unnecessarily. Now let's get back to our issue. We do now have a container that holds our database, our MongoDB, and this container currently stores all the database inside the container itself. Let's have a look. Docker service ps db_server. This service is run on manager 01, and any service and any data that is stored inside this container is stored inside the manager node. If this container was removed for any reason, the data is lost. So we need two things. We need to store this data externally outside the container, and we also need this data not to be bound with manager 01. We need this data to be available elsewhere so that it follows the container whenever it is moved. There are several options by which you can do this. There are several storage drivers that can be used to achieve this, like Flocker, Rex-Ray, and GlusterFS. However, you can also use native NFS, which is the simplest, although not the most robust method of sharing storage among containers, you can just create an NFS share on a dedicated server, and you can use this NFS share to store the container data, and then you can use Docker volume to create a named volume and point to this NFS share, and then use this Docker volume to create a named volume for the container or for the service, and you'll be sure that the container will always have access to its data, even if it gets moved from one Docker host to the other. That is going to be the starting topic of our next lecture, so until then, take care. Alright, hello everyone, welcome back. In this lecture, we are going to use the solution that we have referred to at the end of last lecture, which is to create a separate NFS share on a dedicated server, and to use that share as a mount point for the MongoDB container so that the container will always have its data available even if it is moved from the Docker host where it is currently running to another Docker host. So let's use our SR01 machine as our NFS server. We could have also created a separate machine for that, but let's use this one. So I'm going to install the following. First, install the nfs-kernel-server, which is the NFS server. So it's apt-get install. Okay. Second thing we need to install is nfs-common. Okay, it's already installed. Now let's create our directory that is going to be that is going to serve as our NFS share. So mkdir-p/var/nfs/db-vol, for example, for database volume. Let's ensure that it has the ownership of nobody, just a security procedure, nobody and no group for /var/nfs/db-vol. Okay, now I'm going to start editing /etc/exports, which is the file that is used to expose whatever NFS shares you want to share using your service. Okay, and the format of this file is very simple. It's even giving you an example here. So let's add our share /var/nfs/db-vol, and we are going to enable machines in the subnet of 192.168.100.024, which is our Docker nodes. They're going to be granted read and write access, sync, no subtree. These are just NFS options that will ensure speed and performance. But the last one is the one that we need to have a close look at, no root squash. This will enable the root user from the Docker host to change ownership of the files inside the NFS share. And this is needed because Docker will need to make some changes to the ownership of the files inside the share in order to be able to access them. So no_root_squash will ensure that the root user under which Docker is running is going to be able to change those files from the remote machine. Okay, so now that we have created our file, now let's restart our NFS service to effect the changes. Okay, it seems that we have a problem with the exports file. Okay, this is no sub_tree_check. Okay, restart the service. Okay, now just a quick test. Let's go to any machine in our Docker swarm, any Docker host, and let's try to mount this share as if we are mounting a normal NFS share, just like this, /var/nfs/db-vol. Let's mount it on /mnt. Okay, just needed to install the NFS client. Let's try that again. Okay, if we run df-h, you can see that we have our volume mounted successfully. This means that we can successfully access our NFS share. Let's unmount this. Okay, Now, in order to work with our NFS share, we will need to create a Docker volume for that. We have mentioned in a previous lecture that we have two main types of Docker volumes, a named volume and a bind mount or a bind volume. So we need to create a named volume that will access that NFS share. So I'm gonna use the following command: docker volume create -- driver. It's local. We've seen the driver before. Let's give it a name, dbvol. Now we should add some options. First option is data type is NFS. The second option is the device or the target equal, and notice that we have to add a colon before the device name. This is just how NFS works. /var/NFS/dbvol, then the -- opt again, O equals ADDR equals the IP address of your NFS share, and then another option which is RW for read write, and the most important of which is no lock. This is mandatory for MongoDB to be able to access this share. Okay, press enter. dbvol is created. Docker volume ls. You can see that I have dbvol created here, and driver is local. Now I will need to shut down all the services that I have in order to test this functionality. So docker service rm web server, app server, and of course db server. Okay, so now I have created my volume. I have removed all the services that I have created previously. In the coming lecture, we are going to test creating a normal container, just a single container. We're not going to use the service, just to see how MongoDB can access our remote NFS share. And then we are going to create a service out of MongoDB, and we can see how the service is going to access the remote data on the NFS share. Finally, we are going to modify our YAML file in order to use Docker Stack to create the same functionality. So until next lecture, take care. Alright, hello and welcome back. In the previous lecture, we have successfully created our NFS shared volume, and we also created a Docker named volume that is going to be used to access this volume over the network, over NFS. Before creating a service and before using Docker Swarm to interact with this shared named volume, let's see how a container will be able to access this volume, just a normal container that is based on our MyDB image. Let's see, docker run -d. I've seen this before several times. --name db test, for example. And I won't be exposing any ports because I'm not gonna use the database. I'm just gonna see whether or not the container is going to run. So --rm to remove the container once I stop it. --mount source is our named volume, which is dbvol. Target is /data/db, and actually MongoDB also has another mount point. I'm gonna add it also on the same named volume, and the target here is /data/config_db, which is used for probably the configuration files of MongoDB. Finally, I'm going to use my image, which is my DB. Pressing enter. Okay, docker container ls. We have a container that is up and running, as you can see. And if I go to my NFS share here and I ls var NFS dbvol, I'm gonna see that this directory is now containing files. These are database files that have been created by MongoDB. Once the container was started, it created those files on my NFS share, and notice here the owner of those files is Docker. Docker has successfully connected to my NFS share and changed the ownership of the file and created and changed the ownership of the files accordingly. This is how my container now is running without any problems. The data of this container is stored elsewhere. It's not stored on this Docker host, it's stored on an NFS share. So if I created this container in any other host that has access to the dbvol volume, is going to have access accordingly to the same data that this container has. Okay, so now let's stop the container, db test. Okay, and now we need to replicate the command that we used to create the dbval on all our Docker hosts. This is mandatory because I need the container to be able to use dbval on any of my hosts. So on manager 02, I have to add this command. On worker 01, on worker 02, and also on even on my SR0 machine, because it is a worker. At the end of the day, it is a worker and it can receive the MongoDB container. Okay, so now let's create the service again. So docker service create -- name db_server -- mount. Can add type is volume. Actually, this is the default. The volume here means a named volume because I can add type is bind. Here I'm specifying that I explicitly want to use the named volumes. So type is volume, source is of course dbval, target is the first one, which is /data/db, and my second mount is going to be type is volume, source is dbval, the named volume, target is /data/config_db, and of course the network is blog network. This is going to be based on 192.168.100.30:5000 /mydb. Let's press enter. Okay, and docker service ls, I can see that I have my database server running 1 replicas out of 1. I could have actually increased the number of replicas, but I'm not quite sure how MongoDB is going to run several containers accessing the same data at the same time. The correct way of doing this is to create a MongoDB cluster, and this will be out of the scope of this class. So I'm just going to create one container or one service for MongoDB, and whenever the service is moved from the manager or from this node to another node, we are sure that the data is going to be kept outside of the host on the NFS share in here, so that, let's have a look here. Okay, so you can see here new data has been added because we have created a new container. So whenever this container is restarted or moved to another container, it is always going to have access to the same data. So now we are adding some extra level of resiliency or some extra level of high availability. Now let's go ahead and create the rest of our services, same as we did before. So we have our app server and our web server. Let's clear the screen and start docker service ls. Okay, and now we have all the replicas up and running, the database, the application, and the web server. If you go to the browser now and refresh any of our pages, of course the post that we have created is now gone because the data was stored locally on the container, but now it won't. As we're going to see, let's just test all the IP addresses that we have, ensure that all of them are working. 100, 200, and the workers 10, 20, and 30. All of them are serving our blog. Let's create a post. High resiliency post data shared. This post is saved on an NFS share. Save. Okay, it has been saved. Go to home. Gonna see that I have high resiliency post. This is saved on our NFS share. What I'm gonna do now is that I'm going to shut down the services again. Docker service rm web server, app server, and db server. Okay, so of course now I do not have any services, and I'm going to start them again, starting with the the db server again. The application server and the web server. Just ensure that they are up and running again. Okay, now if I refresh, I'm gonna see that I have my post although the container was stopped, the whole service was removed. When it was started again, I still have my post and everything is working as expected. All my IP addresses are serving the same log application. Okay, now let's get to the final part of this section, which is that using our YAML file to achieve the same result. So let's again do docker service rm db_server, the app server, and the web server. Let's go to our YAML file blog_swarm.yml. And as I mentioned previously in this section, you will have to change a number of things, the most important of which is the name of the image. The image name is going to be prepended by the service registry IP address and port. And gonna also have to change the version of this file to be 3.2 because I'm going to use some features that need this version. So let's get started. Now this is the image, the DB image. I have already changed the name to be prepended by the service registry name. The volumes is going to be different because now we are using a shared volume. So it's going to be as follows. Type is volume. As you can see, it is very similar to what we are writing on the command line, except that it is using the YAML format. Source is going to be db_vol. Target is going to be /data/db, and another type is going to be volume with the source db_vol and the target /data/config_db. These are just the two volumes that are exposed by MongoDB, and I'm just informing Docker Stack that they are going to be accessed via the db_vol named volume, which in turn is pointing to my NFS share. Now, the rest of the file will be kept as it is, except of course for the name of the image of the app and web server. Let's write them quickly. Let's increase the number of replicas here to be 7. And let's increase the number of replicas here to be 9. The network will stay as it is, but the volumes here is going to be different, naturally. We are going to change the volume name to be db_vol because we are using this name now. And let's add the details. Driver is local, which is the one that ships with Docker. Driver_options or OPTS, the ones that we created or that we added using the -o. So we have type is NFS, then O EDDR, or address is 192.168.100.30. Of course, the options are W for read write and no lock. Finally, the device or the path on which this is going to run is, notice that I added a quotation or a double quotation here followed by a colon because the colon here is mandatory, as I have mentioned before. This is how NFS works. The file system must, or the file path must be preceded by a colon in order to work. So it's /var/nfs/db_vol, just like that. Okay, now let's save the file, clear the screen, and let's first ensure that our service is down because we are going to start it using Docker Stack. So it's Docker Stack deploy -c in the name of the file, and the name of our stack is going to be blog swarm. Okay, we have an indentation error in line 13. Let's get to that. Okay, it seems that I have an indentation error here. Save. Okay, and services are created. Let's have a look. Database server is created successfully, the application, the web server. Now everything is up and running. If you go to the browser now and refresh, you're gonna see that I have the application up and running, and also, as you can see, the data now is always available to us since we are using a named volume on NFS share. No matter where our container was created, let's see, Docker services, PS DB service, DB server. Okay, the name is different now. It's blog_swarm_DB server. And now notice that it has been created now on worker 02 instead of manager 01. And yet it still has access to the data. It still has access to the post that we have created. That proves that now we have a stateful container, a stateful service, whose data is going to follow it, whatever host it is running on. It will always have access to its data. Now, congratulations, we have created a high resilience blog application based on a microservices architecture using Docker containers. That brings us to the end of this section. Until next section, take care.
Hello everyone, welcome back. This is the last section of our class Projects in Docker by Avionics. My name is Ahmed, and in this bonus section, we are going to have a look at a topic that is slightly out of the main course of our class. I'm just giving here, as I am mentioning, as a bonus section. It is how to automate swarm creation. The main topic of our class was swarm creation. I want to discuss in this section how we can automate this swarm using one of the most well-known configuration management tools in the market, which is Ansible. So if you are not familiar with Ansible, if you haven't used configuration management tools before, this section might be a little hard to follow, but I will give you a brief introduction to the tool. It is very easy to understand and use, and it will save you a lot of time and effort. So let's get started. So before we start writing code, let's have a little introduction first about what is configuration management. Well, remember when we used the Docker Swarm to orchestrate our infrastructure and to create the containers, and remember when I introduced Docker Swarm, I mentioned that Docker Swarm takes the descriptive approach rather than the imperative approach. This means that you tell it how you want your infrastructure to look like and to behave. You give it a description of your infrastructure instead of giving it a set of commands and asking it to execute them. Same thing holds for configuration management tools, but here we are not talking about containers, we are talking about the infrastructure that will hold those containers. I'm talking here about the Docker host itself, the machine that is going to hold the containers for us. Now, we have two approaches, either to give this machine a set of commands and wait for it to complete them, like for example, install Docker, create the necessary user, create the necessary permissions, and then start the Docker Swarm by launching, like for example, Docker Swarm init, and then join the other hosts, and so on. This is the imperative approach. On the other hand, you can have the descriptive approach in which you are giving it a manifest of what you want your infrastructure to look like. Like for example, I want 3 Docker hosts. One of them is going to act as a manager, 2 of them are going to act as workers, and I want those specific users to exist with those specific permissions, and so on. So that is exactly what configuration management is about. It's like orchestrating your infrastructure. It's the same as Docker Swarm, it's the same as orchestrating your containers, but this time we are talking about the physical layer, or the hosts that hold our containers. So, if we are talking about configuration management, we are talking about PaaS, or Platform as a Service. If you have read anything about cloud technologies, or if you have worked with any cloud providers before, you have for sure heard about the Platform as a Service and the Software as a Service and Infrastructure as a Service cloud models. I'm not gonna delve too much into the different cloud models that exist and the difference between Platform as a Service and Software as a Service and Infrastructure as a Service. But in plain words, PaaS is, as the word suggests, how you provide a platform and then let your clients or the users build upon that platform. So you provide the physical layer of machines and you apply the necessary configuration on those machines, and then you let the client, if you are a cloud provider, you let the client install the middleware like the load balancers, for example, the Docker containers, and then the application and the database. So configuration management tools help you achieve this help you execute this task automatically. It will configure the infrastructure to be ready to host the second layer of the stack, which in our case is the Docker containers. Okay, and since we are using code to describe our infrastructure, we are using what's referred to as IAC, or Infrastructure as Code. This is another term that is used very much in cloud technologies and in cloud providers. And it's also used in the latest trending topic, which is DevOps. In a DevOps environment, developers can deploy their own applications and operators can write code to deploy software. So both teams are meeting in a common area and they are collaborating together to build software. So a developer can use his or her skills in coding to build an infrastructure using code, as we are going to see when we discuss our tool. A configuration management tool is responsible for ensuring that your infrastructure adheres to your desired configuration state, the same as the orchestration system of Docker. It will ensure that your infrastructure looks and behaves the way you want it to. It will automate repetitive tasks like software installation, user creation, permission setting, runtime environment deployment, among others. And the most well-known configuration management tools in the market today are Chef, Puppet, Salt, and Ansible. And I have chosen Ansible for this lab. And the reason why I chose Ansible is simple. It doesn't require a central server, so it can be run from your own laptop. You don't need to install any agents or any control servers for it to work. Just your laptop is very efficient. You are going to manage your servers the same way you do in your daily work, but this time you're going to use a tool instead of using shell scripts. It also does not require any prerequisites on the remote machines other than Python. The only prerequisite that Ansible requires is to have a recent version of Python installed on the remote machine. And Python comes pre-installed already with most Linux and Unix distributions, so that shouldn't be any problem. It uses SSH for connectivity. This means that you do not need any extra configuration if you are behind a firewall. It uses YAML files. This is the same file format that is used by Docker Stack, if you remember. So if you are familiar with YAML, you will feel right at home when you write the configuration files for Ansible, which by the way are called playbooks. It uses Python as its domain-specific language, which means that if you have Python background, it will be a big plus. Most system administrators use Python as a higher-level scripting language. But don't worry, if you do not know Python, that's okay. The configuration is simple enough and it does not use any hard-to-understand code, as we are going to see. And finally, it's very easy to be installed. If you have Python installed and you have pip, which is the Python package manager, you can just use it to install Ansible. So let's start by installing Ansible. I'm going to use my Mac here. So I'm going to use brew to install Ansible. If you are on a Linux box like Ubuntu, for example, you can install Ansible by using sudo apt-get install Ansible. If you are on a CentOS machine, you can do the same thing by issuing sudo yum-y install Ansible. However, if you are on a CentOS, you will have to enable the EPEL repository first, because the default repositories of CentOS does not contain a version of Ansible. And if you are running on Windows, I highly recommend that you run Ansible on a virtual machine that is running some distribution of Linux, because Ansible does not work very well at the time of this recording. It does not work very well on Windows machines. And in all cases, if you do not want to use your package manager, as I mentioned earlier, you can just use pip install Ansible if you have pip installed, which already ships with Python. So you can just use pip install Ansible and you are all set. So in the coming lecture, we are going to install Ansible on our machine and we are going to fulfill the prerequisites that it needs to be able to connect to our remote server and practice our lab. So until next lecture, take care. Alright, welcome back. In this lecture, we are going to start by installing Ansible. I'm going to install it on my Mac using brew. So it's brew install Ansible. Give it a few moments to complete. Okay, let's clear the screen. Ensure that Ansible is installed by typing ansible -- version. Okay, it's 2.4.3, which is the latest at the time of this recording. Now let's move on to the target of this lab, which is to rebuild our Swarm cluster that we did earlier in this class. But this time we're going to automate this process. We are going to use Ansible to automate this process so that you don't even need to log into the server to create the Swarm. We are going to automate Swarm creation and image building and service creation, and we are going to be left with a host that has all the containers running and our blog application up and running. All of this is going to be done using Ansible. So, first things first, I have created this virtual machine called Docker host. Okay, let's set its host name to be descriptive enough. Host name ctl. Set host name. Let this be Docker host. Okay. Let's log in again. Okay. And this machine is a new installation. It doesn't have anything installed. So if I run docker --version, Docker is not installed. So we are going to use Ansible to do all our work for us. But as we mentioned earlier, the only prerequisite for Ansible to get installed is to have Python. And unfortunately, Ubuntu server does not come pre-installed with Python. So if you run python --version, Python is not installed. So we are going to install it. Okay, let's clear the screen, and now Python has been installed. Python --version, okay, it's 2.7.40. Now we need to log into this machine remotely so that we can do our work from our Mac. We are going to connect to the second IP address that appears here, which was 172.16.199.220. Let's do just that. Okay, and it seems that the SSH server is also not installed, so let's install that. I wonder why Ubuntu gets installed by default without the SSH server. I mean, this should be one of the prerequisites for any Linux installation. Anyway, we're gonna install it. Okay, let's go back and try again. Yes. Okay. Once we are there, let's avail the prerequisites for Ansible. First thing is that we need to be able to connect to our Ubuntu machine without using a password. That's because Ansible will run typically in an unattended mode. You're gonna run the tool perhaps on a periodic basis via a cron job, for example, or a scheduled job. So typically no user is going to be present when Ansible runs, so it needs to connect to the remote machine without using a password, since it connects using SSH. So in order to do that, I'm going to create a public and private key. So I'm gonna use SSH keygen. Press enter. Just accept the defaults. I'm not gonna use any passphrases. And now my private key has been created. Let's clear the screen. And I'm gonna use SSH-copy-ID, which is a handy tool in Linux that is used to copy your public ID key to the remote machine. All that you have to do is just enter your IP address and the credentials. Okay, and to the password. Okay. Now if I try to log in to this machine again, it will not ask me for a password, it will just log in, and this is done using the public-private key pair. Don't worry, this is a secure way. If you haven't heard about public-private key authentication before, it is a secure way of connection. We are not compromising security in favor of usability if you are curious. Okay, the second thing we need to do is that we are going to need the user account that will be used by Ansible to use the sudo command without entering a password. So let's verify what this means. Now what happens if I type sudo and type any command, like for example id? I'm going to be immediately asked for my password for that command to run, like this. Once I do, the command is run using the privileged account, which is root. But again, for Ansible to run, if you want to run commands that require root privileges using Ansible, there should not be a password prompt. So, in order to achieve this, we will need to modify a file that is called sudoers. It exists under /etc. Let's go inside that file and go to that line that reads sudo with a %sign at the start. This is the group under which all users that use the sudo command exists. So in our case, the user that is used to log into Ubuntu, the default user that gets created, is in this group, we need this user not to enter a password when it uses the sudo command. So we're gonna add no passwd colon before the last all in the statement. So in the last all in this line, just gonna add no passwd colon before the last all. And save. Now if I try to run sudo with any command, it is not going to ask me for a password. It is just going to execute the command. Okay, let's exit. And guess what? That is all what is needed to get Ansible running on your remote machine. In the coming lecture, we are going to start writing our playbook, and a playbook in Ansible terminology refers to the configuration file or the instructions file that contains the commands or the instructions or the description of your desired state, and you hand this configuration file to Ansible to run it on your remote machine. So until next lecture, take care. Alright, now that we have fulfilled the prerequisites necessary for Ansible to run on our remote machine, we are now ready to start writing our playbook. And a playbook, as we mentioned in the last lecture, is the configuration file or the instructions file that Ansible uses to know the desired state of your remote machines, and it is going to use this playbook to ensure that your machines will always adhere to this desired state. So I'm going to use this time the Visual Studio Code as an editor, and I'm using it because it contains a large set of plugins that will help in writing code, especially playbooks, because if you have noticed, YAML is very sensitive when it comes to indentation and white spaces and so on. So let's go here to the extensions, and I'm going to ensure that I have Ansible installed. And I'm gonna also ensure that YAML is supported. Okay, now let's reload. Okay, now I'm going to open the directory where we have our projects in Docker. Okay, and let's create a new file. Let's call it deploy.yml. This is going to be our Ansible playbook. And actually, Ansible is a very large topic in its own, and whole courses can be made to describe Ansible and how it works and the different ways it can be used to configure servers. An Ansible playbook typically starts with triple dashes. This is not mandatory, but it is recommended just to mark the start of the YAML file. Let's enlarge the font a little. Okay. The first thing you need to add is the hosts. The hosts defines the nodes or the servers this playbook is going to be applied to. You can add as many hosts as you want. So for example, you can add a set of hosts here, one or more hosts, and then add some tasks to this host, and then another host or set of hosts, and then add its own tasks like this, and so on. In our case, it's only one host. So we are going to write all. All means that it is going to be applied on all hosts that are in our inventory file. Which brings us to the next question, which is what is or where should this inventory file be located? Well, the inventory file is nothing more than a text file that contains the IP addresses or the names of your machines. It can be located by default in /etc/ansible/hosts or /inventory, whatever you want to call it, or I can just add it here in my project directory. I'm gonna create a file that is called hosts. And that is the portable approach, as it is called, so that your whole application configuration files are located in the same place. You don't have to search for files scattered here and there. If you want to move your application code from one laptop to another, you just zip the directory with all its files and directories and move it. You don't have to search for files located elsewhere on your system. So I'm going to add the hosts file here in the same directory, and I'm going to add the IP address of our only host in this stack. We are going to create the Docker swarm on only one host for simplicity. It's going to be the manager node and the worker node, and it's going to have all the containers hosted on it. So the IP address is 172.16.199.220. Let's save this file. Let's return to our playbook. The tasks here defines the tasks that you want this playbook to perform. Easy enough. But before that, we need to inform Ansible that it is going to run as the root user, or in other words, it is going to use the sudo command to implement those tasks. So I'm going to inform it by using the keyword become, and I can either say yes or true. Whatever you choose is going to work. And another thing we need to add before the tasks is some variables. So I'm going to add a vars section here. Variables are, as the name suggests, key value pairs that are going to be used for values that you're going to use multiple times inside your playbook. Let's say, for example, that we need to define our swarm address. Swarm address is going to be used when we create the swarm using the swarm init command. So we need to have an IP address for this swarm. Let's add the IP address that we use to connect to our host, which is 172.16.199.220. Another variable that we are going to use is the name of database image. So it's db_image. This is going to be, if you remember, mydb. A third variable is going to be app image myapp. And notice here that I am using the dash followed by a space, and the indentation is twice from the left. This is how YAML works. This is not specific to Ansible. This is how YAML file works. If you want to add an array or a list, it has to be in that manner. Okay, so we have a DB image, an app image, a web server image. It's gonna be called my web server, if you remember. And let's add the DB service name, or the name of the service that is going to be created. It was called DB server. The app service was called app server, and the web server service was called just web server. Okay, let's move on to the database volumes. We are going to need two volumes. So db_data_vol for volume. And let's give it a path to the database. Let's store it in /opt/mongo/db. This is the mount point that we are going to use to store the database or the MongoDB volumes in an outside location. Remember, we mentioned several times before, but this is the only way by which you can persist data stored on a container, because once the container is removed, the data is lost. So we need to store data elsewhere on the system. So this is the path where we are going to bind or mount the database volume. We also need another volume for the config.db. In our last lab, when we used Docker Swarm on multiple hosts, we stored both of those in the same file system. Let's change that this time and let the configuration be stored in another place. So we are going to store it in /opt/mongo/config.db. Those two paths are going to be created later, and the playbook is going to help us in this task as well. Now let's move on to the replicas that we are going to need. So app replicas. We can have 3 replicas for the application. Web server replicas. We can have 5 web server port. The port that we are going to use to listen externally or to mount or to bind it to the internal port. If you remember, it was 8080. And finally, the network name, the swarm network that we are going to create and use it to run our services. We're going to call it blog_network. Okay, so those were our variables that we are going to use in the playbook. In the coming lecture, we are going to start writing our tasks. So until next lecture, take care. Alright, in this lecture, we are going to start writing the tasks. In the previous lecture, we have defined the variables that we are going to need in this playbook. Let's now run our tasks. The tasks are a list, so we are going to have to type a dash before each task. And typically a task will have a name. This is not mandatory, but it is very, very useful because when something wrong happens or when the playbook stops while execution for some reason or another, the task name is going to be displayed before the step where the error happened or where the failure occurred. So we'll have an idea about which task failed and which task succeeded. So let's give our first task a name, which will be install the prerequisites. And our prerequisites are simply Python pip and python-apt. Both of them are needed for Ansible to be able to work with Docker. So we are going to use the apt module. The apt module for Ubuntu, as the name suggests, is going to use the apt-get command to install packages. It needs a name for the package, and it needs a state. So it needs a name and a state. The name is the name of the package, and the state is whether it is present or absent. So as you can see, Ansible is describing the state of your host or of your node. It's not taking commands from you, it's taking a description. So we have a package with a name, and you specify that this package is either present or absent. Either it is there or it is not there. And the command is going to be created automatically by Ansible. You don't have to write any commands here, except in some rare cases that we are going to see later. But in most cases, Ansible is going to create the command for you depending on the description that you need. So, since we have two packages that we need to install using apt, we are going to use a list. So we are going to say name, and we are going to use a variable. This double curly braces in Ansible or in YAML in general defines a variable. An item here is a special variable. We're going to see what it does in a moment. State is installed or present. Both of them are the same. And then I'm going to pass in a special array that is called with items, colon. And here I'm going to type the items that I want to be substituted for by this item. So when I type Python pip, for example, and then Python apt, and when this script runs or when this playbook runs, it is going to loop through all these variables, or actually through both of those variables, and it's going to substitute in the first run Python pip instead of item, and in the second run Python-apt instead of item. Both of them are going to be executed under this task. So instead of writing two separate tasks, we can just use this way or this shortcut for adding as much packages as you need to the system. Okay, the second task is going to install a pip package that is called docker-py. Docker-py is a pip package, so we're going to use pip, Python pip instead of apt. Again, we're going to give it a name. The name is docker-py, and again, the state is present. So instead of just writing pip install docker-py, Ansible is going to do that for you. And again, you can have the state either present or absent. This means that, again, you are describing the desired state instead of writing commands. Now we are moving to installing Docker. So the first thing we need to install the Docker apt repository. If you remember earlier in this class, when we installed Docker, we executed that step. We installed the Docker apt repository, and Ansible can do that for us using the apt-key module. As the name suggests, apt-key is used to install the repository keys. Just give it a URL. In our case, it's https://linux/ubuntu/gpg. This is required because otherwise the apt-get install command will fail because it won't be able to verify the package. So we need this key to be installed. And of course the state is present. Finally, we can install the Docker apt repository itself. Notice the indentation. We need to have the same indentation for all the tasks, as you can see. So this time we're going to use apt repository, and we are going to give it a repo name. I'm just going to paste it here because it's a long one. All this is actually taken from the Docker installation page. You can find all this information on Docker CE installation Ubuntu. we are just automating the process. So we have repo, and this is the name of the repo. But notice here a very important thing. The installation repository URL is requesting that you have this URL followed by the Ubuntu release. Ubuntu has a release name. So in our case, we have Ubuntu Server 17.10, which has a release name of Artful. The repository that we are going to use needs this name in the URL. So in order to grab this name, and because we want this playbook to run on any Ubuntu version, not just a specific version, not just 17.10, but if you upgrade it to a more recent version, or what if you have a host that is running Ubuntu 16, for example, or something, this has to be as generic as possible. So we are using here a special variable in Ansible that is called a fact, or an environment variable. A fact is, as the name suggests, something that is related to the host on which Ansible is going to be executed. Ansible collects a huge number of characteristics about the host that it runs against, like for example, the name, the IP address, the number of network cards that it has, the IP addresses of those network cards, the users, the installed packages, and a lot more. So among the things that Ansible collects is the distribution name. And in order to get this, you will have to enter this variable by adding a double curly braces here and type Ansible underscore distribution underscore release. When this playbook runs, it is going to substitute this variable by the name Artful. And if you have another Ubuntu version, it is going to be substituted for the release name of that specific version. Okay, just to make your playbook as generic as possible. And of course, let's add state is present. Now finally, and if everything went successful, we can install Docker itself. CE, of course, Community Edition. So we are gonna use apt this time, not apt key and not apt repository, just apt, as we did here. But this time we are going to use it to install only one package, so we don't need to have a with items array or list. So we are going to give it a name, docker-ce. Update cache is yes. Update cache is just to let Ansible run sudo apt-get update to update the repository list before attempting to install the package. And of course, the state is present or installed. Okay, let's save the playbook at this point, and let's go to our terminal. Let's clear the screen. And let's try running this playbook just like that, and let's see what happens. Let's see whether or not it is going to install Docker as we instructed it to. And actually, it's a good idea to run your playbook several times when you are creating it, just to ensure that it won't fail in some point or another. And that is one of the merits of configuration management tools in general, which is that if you run the tool several times, it shouldn't make any more changes than the ones that you have already described. In other words, if a package is already installed, it won't attempt to reinstall it. If a file has been changed, it won't attempt to remake that change if that change was detected that it has already been done. This feature is called idempotence, and this is specific to configuration management tools in general. So, in order to run Ansible, we are going to use Ansible-playbook, and we are going to give it the path to the inventory file, which is hosts. We're going to give it the name of the user with which it is going to connect to the remote machine. In our case, it's Ahmed. And finally, the name of the playbook itself, which is deploy.yml. Okay, let's press enter. And the playbook has finished successfully. If you have a look here, you're going to find that Ansible has named each of our tasks with the name that we have added in our playbook. So installing the prerequisites is successful. It is telling you that it changed the host and it's writing the host IP or the name depending on the way you wrote it in the inventory file. Then install the docker py pip package. Then the Docker app repository. Should have renamed this to apt key, okay. And then Docker app repository itself, and then the Docker CE. And the result is that changed 5. We have 5 tasks and all of them were successful. Now if we get inside the machine now, we're going to see that we have, if you run sudo docker -- version, you're gonna see that Docker is installed now. This has been done automatically using Ansible. That brings us to the end of this lecture. In the coming lecture, we are going to start configuring our images, and we're going to use Ansible to instruct Docker to build those images So until next lecture, take care. Alright, so in the previous lecture we were successfully able to install Docker using Ansible. Let's exit from the machine. Let's get back to our playbook. So perhaps we have to change the name of this task to be install Docker apt key or repository key, because this is the key, not the repository. The second task is the repository. Now let's go ahead with our playbook. And notice here that I am not going to delete any of the tasks that have been already defined. If I run this playbook again and it runs through those tasks, nothing is going to fail because it is going to detect automatically that this has been already done. So if you want to reinstall Python pip or Python apt, Ansible will detect automatically that these packages are already installed, so it won't bother and try to reinstall them. Same thing holds for the pip package, same thing holds for the apt key and the repository key and Docker CE package. So again, this feature in configuration management tools is called idempotence. Okay, now let's move on to our next task, which is to build the images of our application. So if you remember, we have three images: the database, the application, and the web server. So in order to build an image, you need two things. You need a Docker file, in addition to any other files that you want to be baked inside the image, and you need to run Docker build. So let's upload the database files or the database image. So upload the DB image. And in order to do that, we are going to use a module that is called Synchronize. Synchronize is going to, as the name suggests, it's going to synchronize two directories, a local one and a remote one. So we are going to specify the source, and the source is mydb. It's in the same directory in here, so we are going to transfer all the files inside this directory, just only the Docker file, to the remote location, which will be dest or destination /opt/mydb. This is going to upload the Docker file to /opt/mydb. Okay, let's do the same thing for the app and the web server. So upload the app image. Same thing, synchronize. The source is my app. Don't forget the trailing slash at the source and the destination to ensure that the content of the directory is what gets transferred, not the directory itself. So the destination is going to be /opt/myapp. Finally, the web server. So upload the web server image. Synchronize again. The source is my web server with a slash at the end. Forget the slash here. And the destination /opt/my-web-server with a slash. Okay, so this is going to upload the files from my local path to the remote path on the machine. The next step is, of course, to build the image itself. So let's add a task, build the database image. And fortunately enough, Ansible has specific modules for working with Docker. So if you want to build an image, you can use the Docker_image module. This module has a name, and the name is going to be the name of the image. Let's use the variable that we have defined, db_image. Remember, we had here db_image that read mydb. We also had an app image and a web server image. Let's use those inside this task. So this will be the name of the image. And if you want to add any variables in a playbook like this, you have to code them in double quotes. Otherwise, you will get an error. Okay, and it also has the path. So the path is /opt/mydb. And let's also build the app image. This is going to have, again, Docker image with a name of app_image and a path of /opt/myapp, because this is where we have our files transferred, our application files transferred. Finally, we have the web server image. Build the web server image, Docker image, name web server underscore image and path /opt/my web server. Okay, let's save the playbook like this and let's run it again. So let's clear the screen and let's run the playbook again. You'll notice that this time it is going to skip the steps that has been already executed. So here it quickly skipped the prerequisites, the Docker CE, app repository, and so on, and it started uploading the files, the DB image, the app image, the web server image, and now it is actually building the database image on the remote host. Alright, the image building process has been completed. We have now 3 images built. The process actually took a few minutes. I had to pause the video and resume it when the build process is complete, so as to speed things up. Now, if we try to log in to the server again, just to check our work. Okay, let's clear the screen, and if you run sudo docker image ls, you're gonna find that we have now images created for us. We have the Nginx image, the Mongo and Node, and our images, MyDB, my app, and my web server. Now everything is ready to start creating our containers, and that will also be done using Ansible. And we are gonna do this at the start of next lecture, so until then, take care. Alright, so now that we have our images available on our remote host, let's move back to our playbook and let's start creating our swarm and creating our services inside this swarm. So, this is our playbook. Let's create a new task. And this task is going to be called create the Docker swarm. Okay, and unfortunately Ansible does not have a module specifically for Docker swarm. So we will have to use native commands to create the swarm. So we are going to use the command module of Ansible. This allows you to execute arbitrary commands against the machine. So it's Docker swarm init --advertise -eddr. Because we have multiple IP addresses on this machine, we will have to choose one of those addresses to be our swarm address. And for that, we have created a variable. If you remember, it was called swarm underscore address. So let's use that, swarm underscore address. Okay. And before moving any further, I want to show you something that is very important when working with this sort of modules in Ansible, the command module and the shell module. Any module that is not native to Ansible is not idempotent, and that is a problem. I'm gonna show you why this is a problem. If you go here in our terminal and let's run the Ansible playbook again. Of course, it's gonna run fast because everything has been done except creating the swarm. So even building the images is not going to take any time because it's going to be skipped, as you're gonna see. Okay. As you can see here, the only change that happened is creating the Docker swarm, and Docker swarm was created successfully. If you want to check, let's log into the machine again, and let's use sudo docker node ls. You're gonna see that, okay, our machine has been promoted to be a manager, and the Docker swarm has been created. That's nice. But watch what happens if I try to run the playbook again. And this is a typical scenario because Ansible playbooks are made to run several times, and they are supposed to run without any failures. Because, as we said, they are idempotent. But idempotence is not available when you run raw commands against the server. So when we run the command docker init swarm, there is no way for Ansible to know whether the swarm is already created or not. So every time the playbook is run, it will attempt to recreate the swarm, causing an error. So let's see what happens when we run the playbook again. Okay, as you can see here, we have an error. Why? If you have a look here at the error code, you're gonna see error response from daemon. This node is already part of a swarm. Use docker swarm leave to leave this swarm and join another one. This is simply telling you that you cannot run or issue the command docker swarm init when this node is already part of a swarm. So How can we avoid such a scenario? How can we let the playbook run as expected? This is where conditionals come into play. Conditionals, as the name suggests, is a condition that Ansible is going to examine before running a task. So, simply, we are going to create a task that is designed specifically to test for a specific condition. Let's name this task is this, or is the swarm created, like this. And we're going to run a command that will allow us to know whether or not the swarm has been created, like docker node ls. Then we are going to use a module or a keyword that's called register. Register is going to take the output of this command, whatever it was, and saves it in a variable that we are going to define. So let's name this swarm created. Okay. Now we have a command that will always going to be run before the docker swarm init command is run, which is docker node ls. The output of this command is going to be stored in swarm_created. And actually, I'm not interested in the content of this variable, although I can examine the content of this variable. However, for simplicity, I can just use when right under the task of creating the docker swarm, when, and then I can refer to swarm created variable, and I'm going to use one of Ansible's templating shortcuts or tools, which is the pipe, and I'm going to use failed keyword. So what this is going to do is that it's going to examine not the content of the variable, but the exit status of this command, because the exit status is stored in this variable along with any text that this command produces. So what we're going to do here is that we are going to run docker node ls, and if this command fails, this means that this node is not yet in a swarm. This means that the swarm has not been created, because you cannot run docker node ls on a node that is not part of a swarm. So if this node is not already in the swarm, it's going to have an error, or it's going to have an exit status of non-zero. So I'm going to examine this exit status, and if it is a failure, if this node is not in a swarm, I'm going to let it join the swarm or initialize the swarm using this command. Okay, so let's save this playbook now, clear the screen, and run Ansible playbook again. Okay, as you can see, this time it has skipped creating the docker swarm. That is because it has examined the command docker node ls, and it has determined that the command exited successfully because this node is already part of the swarm. So accordingly, this command did not fail. So failed here does not exist, or this command did not fail. Accordingly, it will not execute docker swarm init, and it will skip this task, creating the docker swarm. Okay, so now that we have created the swarm, we can start creating our containers. But first, we need to create our network. So create the swarm network. Remember, it was an overlay network, and Docker already has a module for this, so it's idempotent. Docker network. It takes a name. We already have this variable defined. It is called swarm_network. Let's just ensure that that was the name that we chose. Okay, it was called network_name. Okay, it was called network_name. Okay, and the driver is going to be the overlay driver. Now we don't need to add any conditions here to verify whether or not the network has been already created, because this is using an Ansible module. So it will automatically check whether or not the network has been created, and if it's not created, it's gonna create it. If it is, it's gonna just skip this part. Let's save and run the playbook again. It's a very good practice to run the playbook when you are writing its tasks. Each and every couple of tasks, you should just verify that the playbook runs as expected and that there is no errors. It's the same thing as if you are writing a program, just testing the program each time you write some code to ensure that it's working as expected. Okay, as you can see here, it has created the swarm network. And to prove it, I'm gonna run the playbook again. I'm gonna see that it's not going to fail when it reaches the network creation part, because it is idempotent. Okay, as you can see here, creating the swarm network, okay, it is not changed. Okay. Now, in the coming lecture, we are gonna move to the part where we create our containers. So until then, take care. Alright, now that we have our swarm created and our network, our overlay network in place, let's start creating our containers. So we have a database container, and this container needs mount points for the volumes that it's going to use. So before creating the container for the database, we need to create the necessary paths for the DB volumes. Remember, we had /opt/mongo/db and /opt/mongo/configdb. We need to create those directories. So I'm gonna use the file module of Ansible. I'm gonna give it a path. And because I need two paths, I'm gonna use the with items. So a path is equal to item, state is a directory, and recurse is yes, because we are going to create nested directories. Then with items, the first one was stored in a variable. So it is db_data_volume. The second one is db_config_db_volume or vol. Let's have a look here to ensure that we are referring to the correct variables, db_data_vol and db_config_db_vol. Okay, so this module is going to ensure that those directories are created. Let's move on to creating our database service. So create the DB service. And again, Ansible does not have a module specifically for creating Docker services. So we are going to have to use the native command. And as mentioned before, whenever you use the command module, you will have to ensure that it is idempotent. So let's see. We are going to create the Docker service, Docker service. That's just the same command that we used before. Consider this as a recap. So it's Docker service create -d for the background --name the DB service, which is DB server actually. This is a variable --network name. This is another variable that we have set at the start of this file. Then let's specify the mount points. So --mount type is bind, source is db_data_vol, the variable, and target is /data/db. We have covered this before earlier in this class. We have a second mount point. Type again is bind. Source is db_config_db for the configuration _vol, and target is /data/config_db. And of course, the name of the image will be written at the end of the command, db image, which is my db, but this is just the variable. Okay, it's a long command, but it's fairly simple, and we have written it before. But again, if this command is run more than once, it's going to result in an error, because you will be attempting to create a service with the same name as an already existing one. So in order to avoid this, we will need to add another condition here. So name is the DB service created. Just run a simple command to ensure that DB server is not created. This command can be as simple as docker service ps, then give it the name of the service, db_service, and register the output of this command in something like db_service_running. Then in here, just add a when conditional db_service_running has failed. Okay, so let's save this playbook and let's clear the screen and try to run the Ansible playbook. Okay, and notice here that this error stopped the playbook from continuing. So when Ansible tried to ensure whether or not the DB service is created, and it ran docker service ps db_server, and because this command resulted in an error, the playbook was halted. So in order to avoid this situation, you can always add ignore errors, yes or true. Okay, so let's clear the screen and run the playbook again. Okay, this time the playbook ignored the error, as you can see, ignoring, and it went along and created the database. In order to ensure that this is actually what happened, let's log into the machine, type sudo docker service ps db_server, and you can see that the database is running. Docker service ls, you can see that we have one replicas of one running the database server, so we have successfully created the database server using Ansible. Now let's move on and create the rest of our containers the same way we did with the database server. So the first thing we need to do is ensure that the service is running. So is the app service running, and just add a command, docker service ps, then the name of the service, app_service, and register any variable with a descriptive name like app_service_running. And don't forget to ignore errors, yes or true. Then just issue the command to run the app service. The command will be docker service create -d -name app_service -network, and the network name. We don't have a mount here, but we do have a number of replicas to create. So we are going to use the variable that is called app_replicas to create the desired number of replicas, and finally the app image, just like that. But of course, this command will only run when app service running command has failed, which means that the application service or the app service is not running because the output of docker service ps app_service is false or is non-zero. Okay, let's save. Let's clear the screen and let's try again to run the playbook. Okay, again, it has reported that the app service is not running. Accordingly, it created the application server or the app service. Let's again log into our machine to ensure that we do have the expected output. Okay, now we have 3 replicas of the app server and 1 replica of the database server. Now the final one is of course the web server. So name is the web server service running, and the command is going to be docker service ps web server _service register web server running, and of course ignore errors is yes, so as not to halt the execution of the playbook. Now the name, run the web server service. Command to do this is docker service create -d for the background --name web server _service -network name -replicas web server replicas. And here we are going to have to expose ports, so we'll use -p web server port, the port that we need to expose, which is 8080 as we have defined it in the variable section. We have to map this port to port 80 inside the container. Just have a look at the variables here. It's port 8080, okay. And finally, it's the web server image, web server _image. And this has to run only when web server _running has failed. And again, if you're still confused, this is the output of this command, docker service ps web server _service, which is a variable that will be substituted for web server, the name of the service itself. If the output of this command is false, this means that there is no service running that is called web server. Accordingly, we will have to create that service. If the output of this command is true, which will bring the status of the web server service, then this should be skipped. You should not recreate the web server. Okay, so now let's save this playlist, clear the screen, and run the playbook. one last time. Okay, and the final service in our stack has been created. Let's have a look at our machine and ensure that we do have the expected output. Okay, we have 5 web servers, 1 database server, and 3 application servers. If we go to our browser and have a look at 172.16.199.220 port 8080, we're gonna see our projects in Docker blog up and running. Let's go to create a new post, user and pass. We haven't changed those to false. And let's create a post from Ansible automation. And this post is to ensure that data remains persistent, because we are going to destroy this swarm and recreate it again using Ansible. This time we're going to run the playbook all at once and ensure that Ansible will bring back the configuration of our Docker host to the way we desire. So let's save this post. Go to home, ensure that the database does have this post. Okay, post from Ansible. It's working. And now I'm going to go ahead and destroy this stack. So Docker service rm db_server, Docker service rm app_server, Docker service rm web server. So now if I run Docker service ls, I have nothing. I'm also going to remove the network, Docker network rm log_network. Of course, I have to use sudo for that. Okay. Now I do not have an overlay network. I do not have a swarm. I will even leave the swarm, Docker swarm leave -- force. So now I have the Docker host at the very bare metal state that it was at, except that we have already built our images and we have installed Docker. But other than that, we don't have a swarm, we don't have any services running, we don't even have an overlay network. So let's exit. Let's ensure that there is no connection. As you can see, unable to connect. This might be due to an accident, due to an unintentional change, anything that could happen to the host so that the expected configuration or the desired state has deviated from what you want. So Ansible will quickly return your Docker host back to the state that you desire, back to the state that you have described in your playbook just by running Ansible playbook. Just like that. Okay, seems that we need to add ignore errors also in the swarm condition, like this, in order not to halt the playbook. Okay, let's run it again. Okay, notice how it skips the error and goes ahead and creates a swarm, then creates a DB server, the app server, the web server. Let's go to our browser. Let's refresh this page. As you can see, we have our page up and running again. We also have our database up and running, and it retained the data that was saved because it was saved outside the container in a volume. We do have our post. This post is to ensure that data remains persistent. And indeed, it remained persistent. This proves that we can use Ansible to move back our machine from whatever state it was at to the state that we desire. If you have a service that is down, if you have a swarm that is corrupted, if you have a network that has been deleted, all what you need to do is just run the Ansible playbook again with the desired state described in the playbook, and Ansible will take care of everything. It will bring your Docker host back to the state that you desire. That brings us to the end of this bonus section and to the end of this class in Projects in Docker by Idionics. My name is Ahmad. I hope you enjoyed this class, and I hope to see you again in future courses by Idionics. Thank you for watching, and goodbye. Alright, congratulations, we have successfully finished Projects in Docker class by Idionics. Let's have a brief summary of what has been covered so far. In section 1, we had a brief introduction to Docker and a quick start tutorial. That was for those of you who did not have experience in Docker or who are new to containerization concepts. In section 2, we moved on to building images and containers, how to build an image from scratch, how to use Docker build, how to edit the Docker file, how to add files and directories to your image. We built the MongoDB and the Node.js and the Nginx images so that they can be used in our blog application. Then we started running containers out of those images, all on the same host. At the end of that section, we explored the drawbacks of this architecture and how we can address those drawbacks came later in this class. In section 3, we introduced Docker Swarm, the clustering platform of Docker. We made some changes to our applications so that the components could connect to each other inside the swarm. Then at the end of that section, we used Docker Stack to automate the process of creating the swarm using a YAML file. In section 4, we added resiliency to the swarm by moving it from being hosted on just one Docker node to multiple Docker nodes. We created 2 manager nodes, 2 worker nodes, and we also created 1 service registry component node where all our images are going to be stored locally. At the end of this section, we introduced Docker storage in a little more detail and how to handle shared volumes, that is, how to handle the situation when one container is moved from one host to another and it has its storage on a volume that is physically outside the container. In section 5, which was a bonus section, we used Ansible as a configuration management tool to automate swarm creation. We introduced configuration management tools first and where Ansible fits in the big picture. Then we installed Ansible and availed the prerequisites that it needs to work on the remote hosts. We created a playbook and we ran that playbook on a bare metal machine. Ansible proved to be powerful enough to bring a bare metal machine from scratch to a one that has Docker installed, Docker Swarm, and also the images and services up and running. So you can bring a machine from any state it is in to the state where everything is running perfectly. And that was all for projects in Docker by Avionics. I hope you enjoyed this class as much as I enjoyed teaching it, and I hope to see you again in future courses by Avionics. My name is Ahmed, thank you for watching, and goodbye.